All right, very good morning, everyone. Welcome back. Unfortunately, once again, we go online for the day, but hopefully we'll be all together in the building tomorrow. So the first speaker this morning is my friend Xingyu Wu. Xingyu Wu is an assistant professor at the Mind Lab at the Hong Kong Polytechnic University. He made all his way here to then be presenting from the hotel, which is a little bit sad, but hopefully you will get to meet him later this evening. Looking at his CV, it looks like he doesn't sleep much either. So he's really productive. His research is all about automated machine learning, causality-based learning, and large foundation models. And he's a certified champion. He managed to win the first prize on the 2024 IEEE CIS Flame Challenge that was all about LMs for different things. And hopefully we'll hear something about it later today. But what is really terrifying is that he is, well, incredible at service and what we call peer esteem. He is currently a reviewer of over 40 journals and 25 major conferences. That means that, statistically speaking, if you have a submission somewhere else, he has read your paper. So the fate of your submissions are in his hands. He's reviewing this much. Anyway, let's get Xingyu to explain to us all about automated learning in the era of large language models. Thank you. The floor is yours.
Okay, thank you for your introduction, Isaac. Good morning, and welcome to my tutorial. My name is Wu Xingyu, and I'm an assistant professor in the Hong Kong Polytechnic University. It's a great honor to be here to share our recent study on how the large language models are transforming the landscape of automated learning research. I know Prof. Frank Harter has had a presentation yesterday, so maybe he's more suitable for this topic. However, I'm a fan of Prof. Frank Harter, and I have learned a lot from his paper. So I'll try my best to for this presentation. Okay. Over the past 3 years, we witnessed the explosion of interest of LLMs, not just as tools for language or reasoning, but as general problem solvers and knowledge system. So our motivation for this tutorial is simple but fundamental. That is, can large language models not only learn, but also automate learning process itself? Before we discuss this problem, I would like to first briefly introduce the background of the large language model on this slide. As we can see from the timeline, the LLM have rapidly evolved over the past few years, from early models like GPT and BERT to more recent giants like GPT-5, Gemini 3, and Llama 4. These models with hundreds of billions of parameters have grown not only in scale, but also in capacity. So this model have completely transformed our daily life as introduced by Isaac yesterday. They can summarize text, write code, and solve some mathematical problems, and even can guide the decision making in some scientific research and engineering workflow. So their superior performance stems from three main fundamental characteristics. That is the transformer-based language model architecture and tens or hundreds of billions of parameters and the pre-training process on massive data. Roughly speaking, there are four practical capacity of LLMs that are most commonly used, including the rich domain knowledge, generalization ability, representation power, and search ability. Firstly, for the rich domain knowledge, uh, the large language model can acquire rich domain knowledge through large-scale pre-training. During the pre-training phase, the LLMs can learn from the text data across various domains, and they can capture the statistical patterns and the semantic information of the language. So this enables them to obtain the interdisciplinary domain knowledge and handle specific tasks better. The second one is the generalization ability. The LLMs have demonstrated remarkable ability in text generation. Actually, the generation ability is the most commonly used ability in our daily life because we always use ChatGPT to generate everything. It can help us write email, write our articles, and even our code. So uh, that is because the large language model is trained for to predict the next token in a paragraph. So during the pre-training phase, um, they can generate high quality text based on the given context and have been applied in many real-world applications like text summarization, automated writing, and code generation. Thirdly, it is representation power. Um, this ability is more relevant to the training process because LLM can possess powerful text presentation ability, and this uh, generated representation vector can be used in many downstream tasks. For example, we can feed one text into the open source and they can generate a high dimensional numerical vector. And this numerical vector can be used in some downstream tasks. For example, we can input this high-dimensional vector into an MLP and to construct our own model for text classification, and the output of this MLP is a label of the text. And the last one is the searching ability. This ability is based on the aforementioned ability, rich domain knowledge. For example, given a query, LLMs can search for the relevant answers or information from its knowledge base and generates the accurate responses using their generation ability. So just because of this after the emergence of the large language model, when we have a question, we always directly ask the ChatGPT rather than Google it. Okay. What we mainly want to discuss today is how the large language model can empower the automated learning system. Actually, AutoML is a research topic with a long-standing history. So in this slide, I will briefly introduce the research topics encompassed by the concept of AutoML. In this figure, we provide the entire workflow of the general machine learning research, including the problem definition, data preparation, model development, and model evaluation. And in model development, there are some subtasks like data engineering, model training, and model analysis. So the auto the goal of the AutoML is try to achieve the automation of the entire workflow, and at different stage, the goal of AutoML is different. For example, at the data preparation level, AutoML want to automatically select the features and uh, problem and the instances. So the research topic includes the feature selection, feature extraction, and data augmentation. And at the model and algorithm preparation stage, AutoML usually try to automatically select and configure the model and algorithm. So it includes the model and algorithm selection, algorithm configuration, and hyperparameter optimization. Uh, at the model and algorithm optimization stage, uh, AutoML usually discuss some method for self-evolving methods of the models and algorithm. So for algorithm, we will discuss how to automatically design the algorithm. And for a small model, we will discuss the neural architecture search. And for large model, we will discuss automated model merging. So in the following of this tutorial, we will include 4 topics. We will present 3 studies under the model and algorithm selection, one study under the automated algorithm design, and 1 study under the neural architecture search, and 3 study under the automated model merging. So my research focus now mainly on the model selection and model merging. Okay, let's begin our first part. The LLM-empowered algorithm selection. Before we introduce our study, I would like to first briefly introduce the background of the automated algorithm selection. In this slide, we provide 2 examples. The first example illustrates 2 algorithms perform very differently on different problem instance. And sometimes algorithm 1 wins and sometimes algorithm 2. This leads to the most fundamental theorem, that is the no free lunch theorem, which tells us that no algorithm can perform best on all problem instances. So to better visualize this phenomenon, we further evaluate 10 evolutionary algorithms on 100,000 single objective optimization problems, and find that the best performant algorithm vary significantly across the problem landscape. So these 2 phenomena naturally motivates the need for automated algorithm selection. In very early stage, the traditional algorithm selection usually relied on human expertise. For example, the well-known SCIK learn package that use the decision tree to determine which algorithm is the most suitable one for the given data set. And after that, some researchers tried to formalize the automated algorithm selection as a machine learning pipeline, including extracting the problem features, learning the mapping from problem features to algorithm space, and using the performance data as a supervised information. This unidirectional framework is the most commonly used algorithm selection framework before. However, there are some limitations of the unidirectional framework. They only focus on the problem side and takes the algorithm as a black box. So they ignore the abundant information behind the algorithm architecture. So our study is try to solve these problems by introducing the algorithm representation. So we want the algorithm selection model can not only tell us which algorithm is the most suitable one for a given problem instance, but also tell us which types of uh, problems is most suitable for a candidate algorithm. So we try to construct a bidirectional framework for the algorithm selection. Uh, Before the emergence of the large language model, it is very difficult to represent the algorithm because there are many things we need to consider. For example, the abstract syntax tree of the algorithm code and the semantic information and library function in their code. We even need the representation method to understand the background knowledge of the problems and algorithm. So it's very difficult. However, with the help of the large language model, we can directly feed the code into the code-related code pre-trained LLM like CodeBird and CodeGPT to get the representation vector of the code of these candidate algorithms. Even if the code is unavailable, we can also use some general purpose LLM, and we feed some description text or the pseudo code for this candidate algorithm into the general purpose LLM. We can also get their representation vector. One challenge is introduced by the LLM representation is the high dimensionality. We take the most commonly used slib as an example. You know, slib is the most commonly used benchmark for algorithm selection. And in this benchmark, the problem features, the dimensionality of the problem features is about hundreds of features for each problem instance. But the algorithm representation output by the large language model usually reaches to millions of numerical features. So the first thing we need to do is to design a feature selection module to reduce the dimensionality of the algorithm features. In the feature selection module, we first the pre-trained algorithm features will first go through the LSTM to extract their sequential information, and after that, we use the Gowda distribution to model the selection or not selection of algorithm features, and the parameter pi I corresponding to fi, that is each of the algorithm features. The pi I will determine which algorithm features should be selected. Our entire algorithm selection model is shown in this figure. The problem features and algorithm features will go through their MLP, and we can get the problem representation and algorithm representation. After that, we will calculate the cosine similarity between the problem representation and the algorithm representation to determine whether to select this algorithm. Please note that this model should be trained twice. For the first training, the feature selection module will be trained with the entire algorithm selection model. And after that, we can get the value of parameter pi for each algorithm features, and we will know which features should be retained. And we will keep the selected features and remove the feature selection module and train the algorithm selection model for the second time. And finally, we go to the trained model. Our experiment is conducted on the S-lib benchmark, and this table presents the disparities in part 10 score across 10 distinct problem scenarios for different algorithms. The part 10 score is a widely used measure in algorithm selection, and it takes into account both the algorithm solution time and timeout situation. So from the table, we can observe that our proposed SLM leveraging the LLM's algorithm representation demonstrates significant advantage across diverse scenarios. Moreover, LLM's representation of algorithms endorses the model with the ability to generalize on algorithms, which is lacking in existing approaches. To access the generalization ability of SLM, we systematically remove the algorithm and from the training set in this data set and analyze resulting performance changes on the comprehensive test set. Um, the graph here illustrates the remarkable generalization ability of ASI. Furthermore, the graph in the in this figure validates the efficacy of each modules in the model, and these findings underscore the superior performance and generalization ability and the efficiency of each module for our proposed as besides the experimental results, we also want to introduce some theoretical results for the algorithm representation. In this study, we mainly discuss two types of algorithm features. That is the adaptive features and pre-training features. The pre-training feature, just as mentioned before, is output by the code pre-trained LLM. And the adaptive feature is output by the embedding layer. That means we feed the algorithm ID into the embedding layer and train the embedding layer with the entire algorithm selection model, and we can use the embeddings of each algorithm as a representation vector for candidate algorithm. So due to the difference in the acquisition, adaptive features and pre-training features have different pros and cons. For example, the adaptive feature is more relevant to the algorithm selection task because each of its features is obtained by the training process of the algorithm selection model. However, not all pre-training features is relevant to the algorithm selection task because it is obtained before we training the algorithm selection model. So in this study, we try to answer 3 questions from a theoretical perspective. That is, when to use algorithm features and which type of algorithm features to use, and what to be cautious about when using algorithm features. So we provide the following 2 slides to illustrate some theoretical results. I don't detail the proof. If you are interested in the proof process, you can refer to this paper which has been updated on the archive. So in this slide, we compare three cases. That is the model with algorithm features, and classification model without algorithm features, and regression model without algorithm features. The classification and regression means we formalize the algorithm selection as a classification problem, and each candidate algorithm corresponds to one class. And the regression means we model the algorithm selection process as a performance prediction task, and the trained model is to predict to regress the predicted performance. So we provide their upper bound of the generalization error for each model, as shown in these three equations. We can find that as the number of training problem instance increase, that is SP. We can find that the generalization error decrease at the same rate. The main difference is on the influence of the number of candidate algorithms. If we increase the number of candidate algorithms, we can find that the SA, in this case, the SA is on the denominator, and in this case, the SA is on the numerator, and in this case, the SA is not absent. So increasing the number of candidate algorithms will reduce the generalization. But increasing the number of candidate algorithms in this case will worsen the generalization error because the SA is on the numerator, and increasing the number of candidate algorithms in this case has no effect on the generalization bound. So that is the main difference. By these three equations, we can demonstrate the generalization ability of model based on algorithm features under many algorithm scenarios. In this slide, we will compare two types of features, that is the adaptive features and output pre-training features. We can find that when we increase the number of problem instance and candidate algorithms, the generalization error of adaptive algorithm feature-based model decrease at a rate to this term. But for the pre-training algorithm feature-based model, their generalization error decrease at a rate proportional to this term. The main difference is SP to the 1 second power, and this one is SP to the 1/4 power. So the adaptive algorithm features has a better generalization ability. But when there are distribution shift, we can find that the adaptive feature based model cannot generalization on the distribution shift. But in the pre-training algorithm feature-based model, we can find that the model performance will degrade with the generalization gap growing proportional to this term. That is the chi-square divergence between the test distribution and the training distribution. So that means the pre-training feature-based model has generalization ability, which is better than adaptive feature-based model under the distribution shift. Based on these two slides, we can answer the three questions. For the first question, when the candidate algorithm set is large and the test distribution might be different from the training distribution, we should use the algorithm features. And for the second question, when we want to select the best algorithm from a long set of candidate algorithms, we can use the adaptive algorithm features. And when the algorithm transfer or the introduction of new algorithms is expected, we will use the pre-training algorithm features. And for the third questions, what to be cautious about when using algorithm features, we provide three suggestions. Actually, these suggestions come from the theoretical results. For example, when using predefined features, attention should be paid to the numerical stability and the semantic consistency of the feature representation. That is because for the predefined features, pre-training features, this term will be enlarge the upper bound of the generalization error. So we must control the value of this term. So we need to pay more attention to the numerical stability. After we obtain the algorithm features, we can further use these features to improve the performance of algorithm selection. In this study, we try to introduce the causality into the algorithm selection task. So the causality here means because the problem features have certain values and therefore the algorithm features should have certain values. That is the causality meaning of in this case. In this study, we try to model the causality between algorithm features and problem features. So based on its meaning, we only consider the causal link from problem features to algorithm features. The causal learning process is actually to reconstruct the value of each features. So our model is designed based on our assumptions. That is the causal link from problem features to algorithm features. We only need to reconstruct the algorithm features based on the original problem features and its best performing algorithm features. And the reconstructed algorithm features can be taken as the estimated best algorithm features for a given problem instance. So our model is shown in this figure. The problem features and algorithm features go through the causal learning module, and we will get the reconstructed algorithm features. The reconstructed algorithm features and the original algorithm features will then go through their representation module. And finally, we calculate the cosine similarity between these two types of algorithm features. Our experimental results shows that the proposed causal AAs achieve the best generalization ability, as shown in this figure. In different types of distribution shifts, including the problem distribution shift, algorithm distribution shift, and distribution shift by removing algorithm. Okay, let's move to the second part, the LLM-empowered algorithm generation. In this section, we show how evolutionary computation provides a search backbone, while the LLM serves as the crossover or mutation operators for the code of each algorithm. And this hybrid framework enables the automated creation of some novel algorithm. In recent years, the landscape of algorithm design has undergoes a profound transformation due to the emergence of the large language model. Traditionally, the researchers usually relied on their expert knowledge and their brain to craft problem-solving methods within a predefined pipeline. However, these handcrafted pipelines often suffer from inefficiencies and demand substantial domain expertise. After the emergence of the large language model, leveraging the cutting-edge learning models such as ChatGPT, we now have workflows that automatically generate methods tailored to specific problems. However, this code factory is constrained by the performance of the underlying model. If we take the large language model as an agent, we can give its general workflow. So you can find that the LLM-empowered coding agents function as autonomous developers by using a large language model is to navigate this iterative feedback loop. Given a task, the LLM will first write an initial block of code, and this code will be validated by executing it, running it, or through an inter or syntax and style, and running tasks to check for characteristics for correctness. After that, if there is an error in the code, the agents will analyze the error message and linter feedback or test values and feedback this information back to the LLM. And finally, the LLM will generate an improved, corrected version of the code. And this iterative process will be repeated until the generated algorithm satisfied the requirements. These workflows actually have been used in many popular coding agents like Cloud CMD, Gemini, and Cursor AI in VS Code. While many recent works in coding agents present themselves as novel frameworks, but in reality, they merely bolt an LLM onto an existing pipeline while leaving underlying architectures unchanged. So in today's coding agents architecture, I think there are three weaknesses for their design. First, most coding agents operate on the centralized and linear execution models rely on single threaded process with no shared memory or condition structure. This severely restricts scalability and prevents efficient collaboration across different agents. Secondly, human-agent interaction paradigms are fundamentally inefficient. Either the agent assumes full control and risks compounding errors, or human must intervene repeatedly. Thirdly, existing systems overwhelmingly depend on reward functions to guide learning and improvement. However, in some software development, code quality is inherently multidimensional and difficult to quantify. So a scalar reward fails to capture the structural and semantic correctness required for meaningful process. To address these challenges, we propose our method, namely EvoGate. EvoGate introduces a structural shift grounded in a shared graph-based architecture implemented through Git. To better visualize this, we will play a video to demonstrate the principle of the EvoGate.
This is EvoGit, a framework for autonomous, multi-agent code evolution. First, let me introduce its foundation, a version graph that records how code evolves over time. It starts from an initial version, v0 created by a human. From here, autonomous agents takes the wheel. Each agent makes a tiny change to the code base. EvoGit checks whether the new version improves upon the old, shown here with a partial order relation. If accepted, the change becomes a new node in the graph, and the agent continues from there. EvoGit also supports three-way crossover to randomly combine different branches. For instance, v1 and v2 merge into a new version v5. Agents then check whether the merged version is better than both parents before accepted. If a version fails due to regressions or broken logic, it's simply discarded, while other valid solutions remain unaffected, giving EvoGit strong robustness. Development proceeds asynchronously. Agents work independently, without shared memory or scalar rewards, yet still collaborate through the shared version graph. Every change is logged, giving developers full traceability and insight. EvoGit enables scalable and collaborative code generation without relying on predefined scalar objectives or constant human supervision, making it a powerful and practical framework for real-world software development. Now, let me show you a quick demo of EvoGit in action. This project starts from scratch, an empty repository initialized with next.js and a few image assets. At this point, the website is completely blank, no content, no structure. Now, let's switch to a branch developed entirely by an autonomous agent. Immediately, we see progress. The home page now references multiple components. And if we look at the repository, the code is cleanly structured. Each component is placed in its own file with thoughtful organization and naming. Let's check the actual website. Remember, the code is 100% written by AI agents with only text input. The result is surprisingly polished, a well-designed layout, smooth animations, and attention to detail throughout. It even includes the fully functional dark mode, automatically supported with matching styles. All of this was achieved autonomously, with EvoGit coordinating the development through its version graph. What's more, as you may have noticed, this AI-generated project is fully compatible with Git, allowing us to use GitHub as both the hosting platform and collaboration interface. Let's take a look at the repository view. Here, you can clearly see agents branching out after the initial commit, each developing in parallel. Every change is transparently recorded in the commit history, just like in a human-led project. And after hundreds of commits across multiple branches, we arrive at the final version, the fully functional website we just saw.
Okay, to evaluate the EvoGate's autonomous development ability, we constructed two unguided project development experiments. The first one is full-stack web app development. Notably, the system received no reward signals or no acceptance criteria and no external defined quality metrics. Despite this, EvoGate successfully produced a complete code repository featuring modular architecture, refined user interface design, and smooth interactive behavior. So these have been detailed on the video just now. If you are interested in this project, you can refer to our homepage of our lab. Okay, let's move to the third topic, the LLM-empowered architecture search. The third part and fourth part are mainly focused on the self-evolving of deep models. And for small model, we will talk about the neural architecture search. And for the large model, we will discuss the model merging. So the first study is a NAS study. I would like to first briefly introduce the background of NAS. The goal of NAS is to find the most promising architecture from a given searching space. So existing work usually firstly define a searching space and use a searching method like reinforcement learning or evolutionary algorithm to search the best performing architectures in this searching space. So to include as many as promising architectures as possible, existing research gradually enlarge the searching space of NAS. For example, in 2022, the searching space of Auto-BERT has reached to 10 to the 20th power architectures. So searching the best performing architectures in such a large space is an expensive optimization problem. To solve this problem, some researchers try to design some principles to refine the searching space. For example, the first one, P1, use multiple 3x3 convolution layers in early stage to improve model performance. So by introducing these design principles into the NAS space, we can find that the searching space can be significantly reduced. For example, the initial searching space for DARS include 10 to the 18th power of architectures. And after we used the prior knowledge, that is the design principles, the searching space can be reduced to 10 to the 8th power architectures. And after that, we further use some information theory related to the neural architecture search and use the divide and conquer method to search the promising architectures. We can find that each searching space only include hundreds of architectures. So the searching cost will be significantly decreased from hours to seconds. In this study, we try to make this process automated. So in this study, we will use code understanding ability and generation ability of the large language models. We first represent the architectures into the code languages like Python code. And after that, we will provide the code and their performance data to the large language model. And the large language model can automatically summarize the principles from their architectures. The entire workflow is provided in this figure. We first upload the architectures to LLM, and LLM will summarize some principles. The principles will be used to generate some constraints, which is further used to refine the searching space. And after that, the LLM will re-summarize the principles on the refined subspace and repeat this process until the best performing architectures is searched. So our framework can be also extended to knowledge transfer. For example, we can summarize the design principles on one task and transfer the principles to the searching space refinement of another task. And our experimental results show that the large language model can not only summarize the design principles given by experts, but also design some novel design principles. And these design principles have significantly improved the searching efficiency of our proposed method. Due to the time limitation, I will not detail the experimental results. And if you are interested in this study, you can refer to our triple AI paper. Let's move to the last part, the model merging for the large language model. For the automated optimization for large language model, it is impossible to use neural architecture search because the research space is too large. So for the self-evolving target of the large language model, we will discuss the model merging. Model merging, also known as model fusion, is effective techniques that merge the parameters of different models into to generate a universal model without access to the original training data or computational resources. So it is naturally suitable for the multitask scenario. When we talk about the multitask scenario, the most direct idea is to fine-tune the foundation model based on the data related to different tasks. Another idea is to use ensemble learning. The ensemble learning is to combine the outputs of different models to improve the final performance. However, these methods usually restore all these models, and at each time of inference, we need to run all these models. Compared to the model merging, does not need extra training data or the story and computation, story and inference computational resources. So in recent years, model merging has been significantly. We have witnessed the proliferation of the model merging, and there have been it has been applied in many real-world applications like multitask learning, federated learning, and multimodal learning. Existing model merging methods can be roughly divided into three types, including the weight-based methods, subspace-based methods, and router-based methods. The weight-based methods focus on more efficient weight strategies, and they really design better weight coefficients and extend the granularity from model level to layer level. And the subspace-based methods usually project their parameters into a subspace through specification or masking strategies, and then merge to avoid interferences among multiple tasks. The root-based methods usually incorporate the MOE mechanism and dynamically adjust the weights of different expert modules or submodules with their routing network. So our study here try to achieve the modular, fine-grained model merging framework, which mainly focus on two diversities in model merging, that is the diversity in task and the diversity in components. The diversity in task means the varying knowledge demands across tasks. For example, we take the language task as an example. There are some general knowledge which is which will be used on all language tasks like lexical parsing, grammar rules, and syntactic structures. At the same time, there are also some expert knowledge which is task specific and only be used in some of the tasks like segment lexicons and semantic similarity. We provide an initial experimental results here. We can find that if we directly merge the MNLI, the model fine-tuned on MNLI and the model fine-tuned on STSB, there is a significant performance degradation. So that means if we ignore the diversity in tasks and directly merge these models fine-tuned on different tasks, it is harmful. On the other hand, the diversity in components means differences in the internal structures and the functional design of expert models. For example, the MLP layers, norm layers, and attention layers in the usually have different functions and rules. We also provide an initial experimental results here. We can find that if we compare the merged model, which merging all components with three cases. That is model merging without merging attention, without merging MLP, and without merging norm. We can find that the normalization layer has little impact in the model merging task, and the MLP layer and the attention layer has more significant impact. So based on this observation, in this study, we study two aspects of fine-grainedness, that is input level adaptability and component-wise flexibility. The input level adaptability means the model merging results should provide specialized models tailored to specific inputs, and the component-wise flexibility means our merging framework should enable adaptive combinations of components. To achieve such two aspects of fine-grainedness, there are three challenges we must consider, including the combinatorial explosion, cost performance trade-off, and expensive evaluations. To achieve the component-wise flexibility, there is an exponential number of possible model combinations. As the number of logs, models, and components increase, the high-dimensional and discrete search space becomes increasingly vast and may make brute force searching impractical. The second challenge is the cost-performance trade-off. That is because to achieve the input label adaptability, we must keep more expert modules. However, in some resources limited deployment environment, we must consider the trade-off between the cost and performance. So we have to reduce the number of expert modules. And for the last challenge, that is because testing all possible merging solutions in such a vast search space requires significant computational resources. So to address these challenges, we proposed a modular expert recombination for fine-grained and resource-aware merging methods. Our method including two stages. One is the offline optimization, and another is the on-demand reuse. To solve these challenges, combinatorial explosion and cost-performance trade-off, we model we formalize the problem into a bi-objective optimization problem, and one is the storage cost and another is the performance. We first decompose the model into several modules and use an NSGA2, that is multi-objective evolutionary algorithms to solve this bi-objective optimization, and finally we'll construct the modular expert library. In this process, we also design two methods to address the expensive evaluations. We design a merging guided conditional quantization strategy to reduce the storing space and further design a surrogated assisted solution search to accelerate the searching process. For on-demand reuse process, at the inference time, we will design a lightweight router. Guided by the lightweight router, our method can efficiently construct input adaptive models by combining modular experts from the library on demand. So based on the offline optimization and on-demand reuse, our method can achieve resource-aware and input adaptive merging. So fast component recombination without reintroducing additional online search overhead. Due to the time limitation, I will not detail the experimental results. You can refer to this paper. And finally, the second study on the model merging topic is about the architecture merging. The existing model merging methods usually only focus on the parameters and overlook that models in different architectures have broader representation abilities. Although there are some methods involving architecture merging, but as the scale of model grows, computational costs significantly increase and the efficiency of the methods is decreased. So our study try to formalize the architecture level model merging into a bi-level optimization problems. One level is for parameter level and another is architecture level. And in parameter level, we just use existing model merging methods to merge the parameters of different models and generate a universal model. And for architecture level, we use the reinforcement learning. We will train an action network and performance network. The action network will determine which lawyers should be selected and spliced with existing model. And the performance model will predict the spliced model, the performance of the spliced model. And besides this study, we also proposed another study to use the evolutionary algorithm to achieve the architecture merging. In this study, we first used the parameter merging method to generate a universal model with merged parameters. And after that, we add the model to the model repository and use the NSGA2 to search the architecture merging results. And in this study, we also design a glue layer to glue different layers from different models. To better visualize this, we also provide a video, and this is the last study we will discuss. So let's begin the video.
Our overarching goal is to empower researchers, especially those with limited computational and data resources, to innovate and develop LLM architectures even under these restrictive conditions. With our approach, as long as your GPU can handle inference for a certain model size, you can use it to develop a model of that scale. To achieve this goal, we draw inspiration from model merging techniques and propose a novel architecture-level merging method for developing entirely new LLMs. Unlike the traditional pre-trained fine-tune paradigm, model merging does not require vast training data or computational power. Instead, it merges multiple existing models to create a new model. In the merging process, the computational resources only need to support the inference of the merged LLM, without requiring the storage of extensive training data and parameters, such as gradient information and optimization algorithm parameters. As a result, the memory requirements are significantly lower than those of model training. The model merging and optimization process involves 4 steps. First, our method begins with a model repository, treating models as the initial population. In each iteration, models with the same architecture in the repository undergo parameter merging, where the merging weights are determined by an enhanced ties merging with DARE. The merged models are then stored back in the repository and undergo architecture merging. At this stage, we introduce the evolutionary algorithm, NSGA2, which generates new architectures through genetic operations like crossover and mutation. When architectural changes occur, we use knowledge distillation to train an MLP as a glue layer between the merged model layers. The glue layer ensures 2 things. 1, the output of the merged lower layer matches the output of the original model. And 2, the output of the merged layer matches the next layer's output in the original model. Since the supervisory information in knowledge distillation comes from the original model's output, and the input samples for training the glue layer are randomly generated, the training of the glue layer does not affect the data-free nature of our approach. Once the glue layer is trained, all models in the population are evaluated based on performance across various language tasks, and fairness across tasks is calculated using semantic entropy. The final selection is made by considering both accuracy and fairness. We developed an online application to validate the merged models. The application allows users to select multiple models from a model repository and customize each model's weight as well as the parameters for the merging process. Then you can merge them. After obtaining the merged model, users can click a button to conduct validations on various downstream tasks, including dialogue, machine translation, and text summarization.
Okay. This is the end of this presentation. If you are interested in our study, you can refer to these papers. Today's report, you mainly focused on this part and this part. Actually, we have many people, many paper to study the variable relationships and automated feature selection or causal discovery. You can also refer to these papers if you are interested in causal learning and feature selection. In conclusion, I would like to turn my gratitude to the Mind Lab team. Our team is established in 2022 and led by Prof. Tan K. Chen. So our lab, the main focus of our lab, including the evolutionary computation, neuromorphic computing, machine learning, AI for science, and AI for healthcare. If you are interested in this topic, you can also email us to discuss some interesting study. Okay, this is the end of my representation. I think the time is limited, and maybe if you have some detailed questions, you can also add my WeChat or email to me. Thank you, and welcome to apply the postdoc and the PhD position in our lab. Thank you.
Thank you very much, Yinshu. So everyone, I think it's the best thing to do now is we're gonna go for quite some questions. So we are running late, but we are thinking that maybe we're gonna start off the next tutorial at 11:30, right? So we have now a few questions. There are a few in the chat already. First one is from Juan Barea. Juan, if you're okay to unmute yourself and go for it.
Hello. Thank you for the presentation. It was very good. And my question is relation to a paper that it was presented in 2025. It is called Darwin Gödel Machine on the open-ended evolution of self-improving agents, where they improve their performance of AI agents through evolutionary algorithm through time and modifying their prompt. My question is related if EvoGit could use the decentralized Git methodology in order to improve the architectures of AI agents for code benchmarks for code.
Okay. Do you mean the prompt design in this study?
Yes, it was a very similar methodology where they use instead of modifying or merging different parts of code in a Git repository, they modify and merge different prompts for the LLMs.
Okay. We propose the EvoGate is mainly to solve the problems that existing methods are usually designed based on the same framework that is using the evolutionary algorithm as the framework and using the large language model as crossover and mutation operators. So our methods will mainly focus on the architecture for the multi-agent collaboration and do not study how to design the prompt. Yeah.
Okay, thank you.
Oh, thank you.
Thank you. All right. Next up is Yahoo. Please unmute yourself. The questions are also in the chat, Yinshu, in case you want to read them.
Thank you, Xingyu. Very impressive talk. So I just have a question regarding the feature selection on the algorithm. My question is, why do you think that the generation error will depend on the number of algorithm candidates? So for me, it's so ideally, if for example, if we know that there's an algorithm A will outperform all the others, so ideally we should be able to select this out of all the others. So from this point. So why do you think this should depend on the algorithm side?
Okay. Actually, in this study, I think for the feature selection for the algorithm representation, I think the number of candidate algorithm is important. If we only have 10 candidate algorithms, this part is hard to train. So the algorithm feature based algorithm selection model is more suitable for the many algorithms scenario, and in this case we can better train this model.
Okay, I think you talk about the training part, but in the selection part. So if I know that there is a optimal algorithm, so it should not depend on the number of candidates. I mean, you have a result on the generator of the selection result.
The best performance algorithm is means the algorithm in the candidate set achieving the best performance.
Yeah.
If you want to introduce more algorithm, I think the algorithm features can also help in this case, because algorithm features can give the model the generalization ability to algorithms out of the candidate set. And in this case, we need the performance data. If you introduce new algorithm, we need to use the performance data of the new algorithm on different problem instance to further train this model.
Okay, thank you.
Yeah, thank you.
Great. Thank you very much. Ramila, you're next.
Thank you. Thank you for the presentation. My question is, how are you thinking about implementing safeguards in a fully automated agentic system? So with the EvoGate example, we saw the multi-agent tool building a web app. How are you implementing safeguards into that process, for instance? Thank you.
Sorry, can you repeat your question?
So with regards to a fully automated workflow or agentic system, how are you thinking about implementing safeguards or guardrails to protect the user from hallucinations or fabricated actions by the agent?
Do you mean this study?
Just more generally, I guess.
Oh, okay.
If that makes sense.
I think the collaboration of multi-agent is the future of the next generation of AI, because we now have many types of models and algorithms, and they can by the collaboration between these models, we can achieve better performance. For example, in the algorithm generation, one agent cannot do everything for many subtasks in the process of the algorithm generation. If we give them the agent, given the different role to different models or agent, we can let them collaborate with each other. For example, each agent focus on generate or design a specific part of the algorithm, and finally we can got a better and complex system for the algorithm generation. So I think the collaboration of multi-agent is the future of the next generation of AI. Thank you.
Yeah, I think, Xingyu, I think if I understood correctly, Ramila's question is all about what if one of those agents actually does something wrong and says something wrong or inappropriate or that is not correct. Am I assuming correctly that what you're doing here with the agents, you rely on the LLMs to have those safeguarding, let's say, strategies already implemented, and you rely on that because otherwise the whole agentic system doesn't seem to have anything to keep it fair, trustworthy, responsible, safeguarding, and all this stuff. I don't know if that is making sense to you. Ramila, am I right on?
Yeah, there
Yes.
the large language model may indeed make some mistakes for in some cases. So the framework of the multi-agent collaboration actually has many types. For example, one agent is used to check the results of another agent. In this case, we can introduce some domain knowledge or knowledge graph to assist the check process. There are also some other collaboration methods like federated learning. Each agent is responsible for different parts of the system. So I remember there are a survey to discuss the collaboration framework. I remember there were 10 to 20 different frameworks. Yeah. So I think it is an interesting problem. Yeah.
All right. Thank you very much. And there is another question in the chat. I'm going to read out for you, Yinshu, but you can also read it in the chat. So Jaime is wondering that in the algorithm selection part, he's wondering if he understood correctly that you're extracting representations of the algorithms. So he's wondering if you think that it's always necessary to rely on carefully designed abstract representations when using an LLM empower approach.
Okay. To answer this question, I think our theoretical results can be used to answer this question. We can find that there are two cases we need to use the algorithm features. One is the algorithm is there are many algorithms in the candidate. So the algorithm number will help us decrease the generalization ability of the algorithm selection model. You can find that when we use the algorithm features compared with the model without algorithm features, we can find that the SA is moved from the denominator to the numerator. So that means the generalization ability is decrease. Another case is the distribution shift. The LLM pre-training algorithm features can help us help the model to have generalization ability under the distribution shift. You can find that if we use the adaptive algorithm features, that is the embedding output by the embedding layers, the distribution shift cannot be considered in the upper bound, but if we use LLM pre-trained features, the generalization area can be the generalization gap is proportional to the chi-square divergence between the test distribution and the training distribution. So although there also exist generalization ability decrease, but the generalization ability exists in this case. Yes.
Thank you. For me, it's more a general. My question is more a general question about consideration about when using LLM empowered approach, a personal view of you. Not in the case of your work.
So which task do you mean?
Sorry?
Which specific task for your question?
No, a general consideration. If you think that use abstract representation is useful when use a LLM empowered approach in a general context.
Oh, okay. I think the representation of from the LLM is useful for also useful for other tasks. For example, the algorithm generation task. In this task, if we can also represent the algorithm into a representation vector, we can make the entire system trainable. That means in the current in current study, this workflow is driven by the evolutionary algorithm. So if we can obtain the representation of each algorithm, we can train a model to adjust the improvement to predict the most suitable, the best improvement for a given algorithm. And in this case, the LLM representation will help the model trainable. Yeah.
Great. Thank you. Thank you so much for the presentation and your answer. Thank you.
Thank you.
All right. We have 2 more minutes, and there is one more question in the chat, Jinshu. Abel, do you want to read your question directly? We do not hear you now. I can see that you're moving your mouth, but is it not working? Okay, I read it for you. It's in the chat anyway, Jinshu. So the question says, in the applications of the framework to NAS, neural architecture search, do you use a budget to limitate the number of selected architecture that would be evaluated, queried on the benchmark? If so, how big was it related to the other methods that use easy or Bayesian optimization to guide the search?
Okay. Our experiments is conducted on the DARS. So the initial size of the searching space is indeed very large. 10 to the 18th power architectures. And actually, we do not need to search the best performing architectures in such a searching space, because we will use the large language model to generate some principles. These principles will help us directly remove many architectures from this searching space. For example, the architectures satisfies these principles will be retained, while other architectures will be directly removed. So you can find that if we use these three principles, the architecture searching space will be directly reduced from the 10 to the 18th power to the 10 to the 8th power. And the large language model can further summarize some new design principles like P4 and P5. So our searching space will be significantly reduced. Our results is here. You can find that we only need to evaluate 3.9 or 7.6 architectures to determine which architectures is the most suitable. So although the searching space is large, we do not need to evaluate many architectures. Yes, thank you.
All right, thank you. Thank you very much once again, Jinshu, for your presentation. Thank you everyone for the discussion. I think it was really, really nice and productive. So we're gonna take a break, half an hour, 30 minutes. We see each other at 11:30 with Shreyank for his tutorial on zero-shot learning. Thank you once again, and then I'll see you in 25, 30 minutes, 11:30, okay?
Thank you. Thank you everyone. Bye.
See you in a bit. Welcome back. Next speaker is my really good friend Shreyank Gowda, who, I crossed paths with at some point. When I actually left the University of Nottingham, he was coming in, so we actually got to know each other. We got to know each other when I was there visiting the University of Nottingham that I visited so many times, and I still visit every now and again. Shreyank, I think we could say he has completed the Great British Academic Tour, earning his PhD at Edinburgh with a Facebook scholarship, doing a postdoc in healthcare AI at Oxford, and now in Nottingham as an assistant professor. He's got zero rush, but he's going to be talking today about zero shot learning. So whenever you want, Shreyank, the floor is yours. You can share your screen. There you go.
My
Perfect.
screen is being shared, right? Yes. Okay. Hi, everyone. Nice to be in person. I'm hoping everyone's feeling happy that at least one session is great. Yeah. So, Isaac gave an introduction, but I'll do a little bit more. I'm originally from India, so I did my undergrad there. I did my master's in China. I did my PhD, like Isaac said, at the University of Edinburgh. Then I spent a year doing my postdoc at the University of Oxford, so medical imaging. I talk a little bit about my research. Right now, it's been about like 15 months, and I've been an assistant professor in the School of Computer Science at the University of Nottingham. So, very on an extremely high level. So I break my research down into four, I call them pillars. So today we're looking at zero-shot learning, so it will fall under one of these pillars. But in general, I do efficient, sustainable intelligence, learning from imperfect and limited data, robust and trustworthy AI, so jailbreaking LLMs, adversarial attacks, and so on. And I apply a lot of these things that I do into medical imaging and medical AI and so on. So today I'm not going to speak so much about research. So it's going to be more like a hands-on tutorial in like doing zero-shot learning. So we'll walk through something, but I'll also try to explain different steps of it and so on. So we're going to look at what is zero-shot learning. We're going to look at like approaches to solve it, and basically on a very high level, two approaches. We'll also look at some actual applications of it, so something that people have used. So I think Isaac was talking a lot about emergent abilities and so on, and that's like one of the things you want to do in general purpose systems. And that's basically, in a way, zero-shot learning. So you're trying to learn new tasks that the model has not been trained on. And of course, at the end of all this, thanks to Juan who's sitting there, we have a tutorial which is going to like build our own zero-shot learning model. So we'll come up with this hypothetical scenario, and then we'll try to walk through a way to do it. Okay, so as the theme of this school is about general purpose AI systems, so I thought I would start a little bit about it. And what we are right now, or at least what people think, people who are not doing PhDs and people who are not really experts in all this, they're assuming that we're at a stage where we have these robots that can do magically multiple different tasks. And I guess that's the whole purpose of this whole winter school as well. But in reality, what we are actually seeing, can't pour a cup of coffee, can't open a door. So this is what I would say we are when Isaac talks about general purpose systems. I feel like we're a long way from it. So like his definition of being, say, modest is kind of nice in the sense that we're nowhere near AGI is my point. So what AI models are really good at is that they're really good at like taking some data, learning patterns across it, right? That's pretty much what we have seen so far. So we can think of it as, say, that one student in class who he can answer every question that's coming from that particular textbook he studied. But the moment there's something that comes out of the textbook, he has no idea what to do. So this is pretty much what the state is currently. And how we solve this is we keep adding more data, we keep retraining and so on. Or at least that's how we used to do it before the idea of zero-shot learning, few-shot learning, and so on. So again, along with the theme of the school, we came across, I guess Anurag was speaking about scaling laws, and different people here have worked with like all these big LLMs and so on. But the reason that a lot of people got that initial big boost in performance was because, as you can see in this graph, like over time, the number of parameters of these models have been significantly increasing. So somewhere in 2020, we had like 11 billion parameters. Now we're talking about like, I think Google released something which is a 1 trillion parameter model. So we're going at a scale which is not good. And the reason I'm going to talk about all this is I'm trying to motivate why data efficient learning is important, right? So the going in this path of unsustainability and the way things are improving right now is people like industry, and I did speak about this with Anurag yesterday. Industry has a lot of money, so they're able to like come up with like even more bigger models, come up with like that's the solution a lot of the time, right? And I guess DeepSeek was one example which showed this is not necessarily true. So as part of my research, I do something called Green AI. So Green AI is like you want to make your AI models less carbon emissions and so on. So I'll just walk through some examples, and this is like what I consider problems with scaling. So here you can look at, for example, a person flying from New York to San Francisco, the amount of carbon emissions, or like if you own a car, the entire life cycle of that car, including the fuel emissions and so on, you see something like 126,000. But then when you use a transformer architecture and you do neural architecture search, so this is a common problem. A lot of people work on this particular domain of neural architecture search. The emissions of just this one thing is like 5 times that of the entire car's lifetime, right? So this is not a good way of moving forward. And so I have this really nice figure from one of my own papers. So this is about how much electricity we estimated models to use. So you can look at like super efficient models like the mobile net, which is supposed to be working on your mobile phones. It's supposed to be that good. One training run for it is equivalent to like a ceiling fan running for a month nonstop. And the more popular models like the Vision Transformer, so JFT is like the data set that Google owns. But if we wanted to train that Vision Transformer huge on the entire JFT dataset, the amount of electricity is like 147 houses in the UK, the electricity bill for a month, basically. So it's insane. And when you think about it, this is like one run, right? And then you do hyperparameter search, you do optimizing of these models. So you can think of these like being significantly worse. So, and this is again images. So people work with here JFT is like maybe like 1 million something images. Text data sets are like billion data points. Videos are like time along with frames. So it's just unsustainable. And for me, the reason this is all like a big personal motivation. So these models are hosted in like data centers somewhere. And then once these models are, once those data centers heat up, they use water to cool those data centers down. And for me personally, where I'm from, we go through these like phases of water shortages. So it was quite mind-numbing for me to see these type of numbers come out. And so it's personal motivation for the research that I do. And I'm sure at this point, everyone here knows ChatGPT, right? So I'm sure maybe on a daily basis, people do use it. So one conversation with ChatGPT, roughly that water bottle. So half a liter of water for one simple conversation. To train the GPT-3 model, now again, this is like maybe 3 years ago, but to train the GPT model, they needed 700,000 liters. Again, this is an estimation, but 700,000 liters is a lot of water, especially for countries where we go through water shortages quite often. And it was estimated that if these models were trained on instead of in the US and like Asia Pacific, where still not so much renewable energy and so on, data centers are not super efficient, it could be significantly worse. And I spoke about like how much electricity the Vision Transformer consumes, and any guesses of how much ChatGPT's estimate is? Like one training run of GPT-3. Thousands? 17,000 houses. So this is one run, right? So GPT-3, and of course, ChatGPT is one LLM model in one company, and then there is Anthropic, and now there is Microsoft having its own, all companies having their own LLM data. So this is not a sustainable thing to do. So when I say I want to make AI greener, I looked at two ways that I can do this. And one obvious thing is to like what DeepSeek did. Use like smaller models, then your amount that you need to train these models is less. They're not so parameter heavy, so electricity is less. The other, the most obvious one, is to reduce the amount of data we use to train the model. Right. So if we see, again, this is from the same paper which had the houses and so on, but basically it's almost linear dependency. So less data, of course, it's going to be going to use less electricity. So, and for us as humans, we need very limited data to remember something. So we'll do like a short quiz, but you'll get the gist of why the motivation for people like me, Isaac, a lot of his work in topics like zero-shot learning and so on. So how many of you can guess like the animals that are there here? Easy, right? Everyone knows it. Supervised learning. No. I don't know this really, sir. So the reason we know this is it's basically supervised learning. We have seen images of these animals so many times since we've been kids growing up. So it's quite easy to guess these. So now I show you these. There might be someone here who's an expert in animals and who's going to tell me this, but if you do know it, do not say anything right now. But if I ask which of these is an ii, can anyone guess which of these is an ii? No? It's not really I'm not expecting anyone to answer because, of course, it's a hard thing because it's one of the rarest animals in the world, right? So now I give you a clue and I say that it's a long-fingered lemur with rodent-like teeth and a special thin middle finger. Okay. So now it's quite obvious, right? So you can rule out a lot of your examples. You know what your II is. And this is exactly what zero-shot learning is. Okay, so we in this whole tutorial, we're just going to look at image classification. Of course, we look at applications beyond it. But the idea of zero-shot learning is simple. Now, at this point, I can meet you guys, say, like, before I leave on like Friday or Saturday, and I just show you an image of an eye and ask you what this is, you're going to tell me, right? Because it's really easy. Now you know that one thin middle finger is enough of a clue to remember this, hopefully, for the rest of your life. And that's how, for us, it's, as humans, I say this, it's really easy for us to remember these things. Now, of course, it's much more complex for machines, and we'll come to that. But to motivate it, it's basically pattern recognition with no training examples. And it's solved by something called semantic transfer. And we'll look through some ways that this is done. And especially these days, it's become really easy to get the semantic knowledge through LLMs. But before, there was Wikipedia. And I'll go through even before that how things were done. Okay, but before we reach again, like motivation for it. So say we had a data set and we wanted to annotate it. So scale.com is like, I guess, one of the big AI startups in data annotation. So say we want to do semantic segmentation. Per image, $6.4. Maybe not super expensive. 1,000 images, $6,400. Already quite bad. But then we work with like millions, right? So it's not sustainable to do this. And also at the same time, we have so much unlabeled data, we can find ways to make sense of this. So these are like two other motivations that we need. But once a model is able to do this sort of zero-shot learning, what we're expecting it to do is like it becomes scalable. It's able to adapt to evolving information. You come up with different domains, things it has never seen, basically. And again, we'll walk through an example with it. But it's also where, when you look at it, it's moving beyond plain images into sort of multimodal stuff, right? Because you're trying to go beyond pixels. You're trying to relate with that hints that I spoke about, the semantic hints. Now, again, very quickly, we know, I'm assuming most of you here know what supervised learning is. So we have this training set, test set, both coming from the same domain. Anytime there is an image that comes out of domain in supervised learning, what you would do is you would end up retraining the whole model with this new class, and then you have to keep repeating this. And again, this is also not scalable because every single time you have a new class, you can't just keep retraining your model. So how machines learn to do this is one way, and we'll, like I said, we'll speak a little bit more about other ways. So say you have an image, you have something we call attributes. So in this particular example of trying to distinguish between a dog and a bird, you can think of 5 attributes. And now, realistically speaking, this is not going to hold. You tend to work with like 300 or so, which is the example we work with. But just for understanding, you have an image, you have some attributes. So what we want is the model has to be either able to take that image, predict those attributes, or given those attributes, predict what the feature of that image would look like. Understandable so far? So then it becomes much easier. Like if you go back to the previous example, if we wanted to scale our model up instead of adding new classes each time and retraining, we would have this image and an attribute. So a model that does, instead of classification, it's going to do regression of each attribute in the simplest sense. And once you do that, you can pass an unknown image, like say an image of a cat, and it's going to predict something. And we will see how this matching is done later on again. But with those attributes, it's easy for us to tell from the list of unseen classes, whether it's a cat, whether it's a horse, and so on. So I just gave this like toy example. Realistically, you see much more detailed annotations. So again, it's like just 2 examples of a polar bear and a zebra, and you have like a set of attributes. So like I said, we don't work with like 5. We typically work with anywhere between like 80 to 300. So these attributes are like a lot more detailed. So say now, assume I don't have these attributes. So then what would be the most straightforward way for me to do zero-shot learning? Any idea? No? So have you heard of like the word-to-vec model? Yeah, so you pass like a word to it, and it's going to give you a vector embedding, right? So before, like these data sets that I've been showing examples, you have manually annotated attributes. Now, when I'm speaking about zero-shot learning, and I'm saying I want to add a new class, every single time I add a new class, I need someone to manually annotate all those list of attributes again. So that's also not feasible to do. So the first thing, and this is like, of course, years ago, now with LLM, it's a lot different, but what people would do is that they would pass the class name to word2vec and then get a vector embedding of the class name. So that is going to be treated as a semantic attribute. So that's how we're trying to distinguish class names in like a latent space. Makes sense? So how word2vec works, I think most of you have an idea. So like if you look at this example, it's basically saying king is to queen is equal to man is to woman, but you also at the same time see queen and woman are closer to each other than king and man. And it's the same thing you can see with like verb tense, you can see country capital. So this is the nice thing about word2vec. It's trained on a lot of data and it can do this type of matching. Say I have this. Now, if I have a cat and a lion are probably going to be closer than say a cat and a table, right, in this space. So you don't have your attributes, you can still do that sort of matching. So I spoke about this one example of word2vec, but if I had multiple words, so during my PhD, I worked with like video classification, so action recognition, so it's not one word classes. So like animals, it's fine, you have zebra, horses, and so on. But if it's multiple words, what can I do? Imagine we're not in this LLM space, right? So we're still at like word2vec. So what would you do if you have like multiple words? I would say the most obvious thing is to like just take the word embedding of each word, and then you can average out and get one there, right? That's the most obvious thing. So you can average it. So like, for example, if you see the left image, this is like with word2vec, and then you can also use something like sentence2vec, so then it has more context. So you move a little bit from word2vec to sentence2vec, and so if you see word2vec, so shoot ball and shoot gun, if you're averaging out word embeddings, you're seeing shoot and they're going to be closer to each other, but shoot ball and shoot gun are 2 completely different activities, right? So then you move from that, you do sentence2vec, and then you get more context, and then you see that, for example, shoot gun, shoot bow, these all are ending up closer together. An even nicer example is like with this pommel horse and horse riding. Pommel horse is like an Olympic sport. It has nothing to do with horses. But then you use word to vec, it's going to take horse as one of the words. So then there is going to be a lot of emphasis, and it's going to be closer to horse-related classes. Right. So I'm just introducing like how things have changed over time. So people move from this sort of word embeddings to like sentence embeddings, and the people did the most obvious thing. From there, use a knowledge base such as Wikipedia. So again, I'm speaking about action recognition. So say you have the class hammer throw, what they did, and which is why I've left the space on the right to say what they did wrong. But I've taken an example here. So you see hammer throw, what they did is they take each word, pass that through Wikipedia, and then return the definition of it. So hammer, it returns the definition of hammer, and throw, a definition of throw. But again, no context, right? So it doesn't make sense. So this is not really hammer throw. So this is like something we proposed, which was about using descriptions of an action, like steps to do an action, and how you can move from that point of like no context, like in hammer throw, and now you know the first part is that it is a field and track event, and then you have steps to do it, and so on. And of course, now this was like in 2024. The right side was a paper I published, but now people have moved away from this as well, and they just use LLMs for everything, right? And there is, of course, hallucinations, and people are not looking that much into it, but not the point of this talk, so we won't really delve too much into it. So now is the idea of zero-shot learning and everything clear, right? So we'll go into our hypothetical situation, which is what this tutorial is hopeful of helping to solve. So say we have, we're trying to help some island where they have a nature reserve. Say we have like 150 birds. We know what those 150 birds look like. We have some expert who's going to tell us some descriptions of these 150 birds. And now there are 50 new arriving species, which we don't know if they're endangered. We don't know if it's like a new species. But then that expert has an idea of like what these species might be. So again, we have annotation of it. We just have no images of it. So what we're going to do, this whole thing is exactly what we saw in terms of zero-shot learning. We're going to have a trained model, which is going to take some example photos. We'll have the semantic space with these semantic attributes. And the semantic attributes are going to be along these lines, like whether it has a long beak, white color, large wings, and so on. And we're going to test it. And we will go to the testing part a little bit later on. But to start with, you can scan this QR code if you'd like. It's going to take you to a notebook. Do not edit the notebook. I think everyone has edit access, but do not edit it, at least for now. And the first thing we're going to do is we'll have to download some data. Okay. So you don't need to do anything for now. Maybe you can just see the tutorial, and then afterwards you'll of course have access to this and you can do whatever you want. So we're going to start, and this is going to take a few minutes, which is why I came to this part before we go back to the slides. So all I'm doing here is, where I hide this. So all I'm doing, what? Do the same thing. So all I'm doing here is I'm downloading a data set, and also at the same time I'm downloading some pre-trained features of that data set. Okay, so we'll come back to it. So basically what we're going to see is we will see later on some oops. So what we're going to see is we're going to see images like this of like different birds, and they have like a set of attributes. So in total, they're going to have like 312, if I'm not wrong. But these are like some examples of what the attributes would look like. It's going to say like, what's the forehead color? What's the breast pattern, color again? head pattern, back color, wing color. So you have a lot of different attributes, and they're going to all we're going to do the most simplest form of zero-shot learning. Okay, so how this works? I told the example already before. Say we have these scene classes. We're going to take this. We're going to take a model. For now, just imagine this to be any CNN. This is one way, and we'll look at another way to do it. But you take a model, you pass these images. You're going to like make the model predict a set of attributes, and this is what we can do with scene classes. And then after the training phase for the unseen classes, I showed this before as well. Pass images, predict attributes, and then once you have those predicted attributes, what you can do is you can do like a nearest neighbor search. So this is like the most simplistic way of doing it, right? So this is like a very limited example. Tiger and not the orangutan, and dog is close to the lion and not the orangutan again, which I would say kind of makes sense. But again, it's a very limited example. But this is the gist of it. So you predict this, and then you do a nearest neighbor search. Doesn't really, I mean, it does matter, but like or deep embedding model. So what they're going to do at train time is like take scene attributes, predict feature vectors. Okay, and so this is probably easier to understand now. So say you can think of this as like two things running in parallel. So for the scene class, we're going to get real features. So you have like a pre-trained con network. So in this case, it's a ResNet model. I don't know how many of you are familiar with it, but just imagine it's like a neural network that's going to take in an image as input and predict some features. And those features are going to be 2048 dimensions. And now what's the part of the zero-shot learning is there's this model called DEM, which is a deep embedding model. So we're going to pass the attributes to that. Once we are giving these attributes, what the model is going to do is a really small neural network, which is going to take these attributes and again predict out what the feature should look like for those attributes. So it's both sides. We have 2048 dimension vectors. All we're going to do is like use MSE loss to match these, right? And then we're going to do backdrop. So this is training, and now we can go back to the node. Okay, so this is the architecture of the neural network that we're going to use. It's really simple, just two hidden layers. And it's taking, like I said, a 312 dimension semantic attribute, some intermediate representation, and it's going to predict what the visual feature should look like. And this is the same figure that I just showed. So we start with like basic imports. I'm assuming most of you are like familiar with PyTorch and stuff. So I will not have to like walk through things. But so here we have like normally in your dataset class, you would just have labels and like say features or images. But here you're going to have the attributes as an additional tensor. And since you only want one attribute vector per class, then that is the attribute used here. And all images of the same class is going to have the same attributes. So you can just pick any one class, any one example to match the attributes for that class, right? So that's all we're doing. Yeah, that's what we're doing here. So once we have it, we're going to load the features and the attributes. So again, dimensions are matched here. And right now, what we're doing is we're splitting this data set. So because this is like we have like a data set of 200 classes, and we're splitting it into like 150 and 50, where 150 is seen and 50 is unseen. And so we've split, we have roughly 7,000 images on training and 2,000 or close to 3,000 at test time. Okay, everything's moved to CUDA. This is the simple network, which is like 2 linear layers. It has like 2.8 million parameters. So we'll come back to the KNN classify later on because that's like test time. But for now, we're just going to define this model, say 150 epochs. It's quite fast, so it's not going to take much time. Yeah. So now go to the train loop. As you can see, it's really fast because of how small the network is. And so again, trainers, we're just doing MSE loss between trying to max features, right? So yeah. We could potentially train for longer, but for now we just stop here. So how do we test? Okay, so we completed the training part. So now at test time, from the unseen classes, we already have the attributes, right? So we have this DEM model now. We pass those attributes. We generate some feature vectors for those, what would be like a visual class prototype, basically. And then all we'll have to do is like given a test image, we use that same frozen resonant model, get a visual feature, match it with nearest neighbor search to these visual prototypes. Make sense? So we go back.
Shreyank, there are some people in the chat wondering what other approaches we could use instead of KNN for attribute feature matching.
What other approaches?
Yes, is there any alternative to KNN?
Yeah, you can use any like neighbor search approaches. You can use like, you can just do distance matching, for example. But again, this is like the simplest thing. We'll move to like other approaches as well later on. But for the purpose of this tutorial, we'll just look at this. So for evaluation, okay, so we generated visual prototypes. We got an accuracy of 49%, which is not bad. So these are like images the model has never seen before. 49% is not the best, but it's not too bad, I would say. What we can then do is also look at each class and then plot. So we can see that certain classes, the model is super confident. So we look at some examples as well later on, but it's doing really well for a few classes, and then it's, of course, doing really poorly for a few classes as well. So if we, so the worst class it says is this, and that it has like a 6.7% accuracy, which is like really low. So if we load the actual images, so these are classes that it's clearly doing really well with. And I would say the features are quite obvious, right? You can see this like green color, which is like very dominant in most images. Here as well, the white and black, the patterns on the feathers. Again, the color is really easy. So if we look at the worst performing ones, technically you would hope that the model can catch this, but as you can see, there is maybe the lighting is affecting the way the model is predicting the attributes. So of course, there are like a lot of hypotheticals we can do, but we can look at these examples in that sense. So like again here, like the lighting is blocking out the most prominent features. Here, those colors are not obvious at all in the second image. Right. So these are like I would say some examples of like where it's not working. Okay. So that was like we basically did I would say maybe like a 7-year-old paper. So it was like one of the first approaches to zero-shot learning and so on. Now, this whole approach that we did is something called embedding methods, right? We're taking visual features or semantic features, and then we're trying to match those embeddings with some different forms. So these are all embedding methods. Now, so if we look at what are some problems that could occur, most obvious, there is like a latent space that we need to use. So there is a lot of dependency on that latent space. So initially, this paper that I showed was like one of the first that did attribute to visual. Before that, it used to be visual to attribute. But in either case, you either go to the visual space or you go to the semantic space or you come to a space in between. So that space is very key. Now I showed some examples. So there is no guarantee that there is this transfer of space, right? So unseen classes, you saw 6% accuracy, not great. There is also something, it's a very popular problem called hubness problem. So we'll see a small figure later on, but at times when we want to do that nearest neighbor search, there may be too many points that are nearby. And right now, where we have 200 images, all of birds. So if we move from birds to say like different animals or like animals and say non-living things. So that domain transfer is going to be really hard to do in this sort of attribute prediction sense. So this is what I was talking about in terms of like too many nearest neighbors in the embedding space, everything becomes really compressed. And this is the hubness problem, where if you move like these images in that example space, they're like well separated, but then the moment you move them to the legal space, it becomes really cramped up and there are like multiple near neighbors and then you need to make the choice. So up until this point, what we were seeing was something called zero-shot learning, where we had like a clear distinction between the train and test. There was no overlap between the unseen and seen classes. But what you actually want to do is something called generalized zero-shot learning, which is at test time, you're going to have both the seen classes and the unseen classes. So you need to be able to predict both. So at training time, you might have like, say this in this particular example, polar bear and zebra. And in zero-shot learning test time, you'd have otter and tiger. But now you need to have, for generalized zero-shot learning, otter, polar bear, zebra, tiger. Okay, so in this particular approach, the embedding methods would fail massively because they're extremely biased towards the seen classes. You're trying to match attributes of the seen classes to start with. So how many of you here are familiar with like GANs and generative networks and so on? I'm assuming most are? Yes. Yeah. So you can skip the slide about what they are, but so you can move from this embedding approaches to feature generating approaches. So if you think about feature generating approaches, all we're doing is we're trying to learn given an attribute. So you're conditioning on an attribute, you're trying to generate synthesized features. And this whole architecture of a generator discriminator is basically a GAN, which over time you want this generator to be able to synthesize features that are as close to the real features that are available. And of course, it's conditioned on this attribute vector, and you only train this whole thing with seed classes. And what you would do once this whole pipeline of training is done, at test time, you give unseen attribute vectors. The generator is supposed to generate synthesized features. So we have synthesized features for unseen classes, and then we would have seen class features. And then this whole problem just becomes a supervised learning problem. Right. So with this now, we can get over the hardness problem. We can also at the same time do the generalized zero-shot learning approach much better because you're generating features based on those attributes, which are going to be more well separated than in your embedding space. And so these are like the general two directions. Of course, like I work and like I have one who also working with these kind of problems. We do a lot more detail. So this is extremely high level, just to give an idea of like the things that people do. So today, with the issues of LLMs and everything, now the issues that LLMs are creating is translating into zero-shot learning as well. So the first problem is something called data contamination. So now I said in the beginning that I'm using a ResNet model that is pre-trained, and I'm splitting randomly into 150 and 50 classes. Like no one questioned me. But that pre-trained model is on like a larger data set. So technically the 50 unseen classes, it could have seen at some point, right? If it has been pre-trained on a larger data. And now in research, the way we do it is we make sure that split the unseen classes the model has never seen before. But with models like Clip, I don't know how many of you are familiar with, like with OpenAI's and their data issues, a lot of people use their models, but we don't know what those models have been trained on. So that's what I call data contamination. And I spoke about this seen and unseen domain shift. So there is always going to be a bias to seen classes because your model is conditioned on it. Like whether it's generative, it's better than embedding, but still you have the same issue. The hubness problem we spoke about. And there are the semantic representations beyond manual annotations and LLMs with their hallucination. There's a lot of limitations because of the dependency to this. And so a lot of times you see papers where they do not tell you what setting exactly they're doing. So are they using unlabeled data to train the model? Then the setting changes. So it's no more the same setting as someone who has no access to that unlabeled data. Right. So we will do now real applications of zero-shot learning. So it's not image classification anymore. So if what this model is going to do is I'm going to give it, if it loads, yeah, okay. So I'm going to give it an audio of one of my own, which is like from a previous paper of mine. Oh, can I unmute myself?
I think so.
No, I can do it. I just think the echo might be.
You can do that, but possibly you should mute the telly because probably the TV is on, right? And that's why you're having feedback. All right. We do not hear anything, Shreyank. We don't hear you. There you go.
Is it
yes,
audible?
all good now.
Okay.
Yes.
So I was just saying, so this is my voice from one of like a presentation of mine that I'd done before. And I speak no Japanese, so I don't know Japanese. I'm going to give a target text. So this model has never been trained on my voice, so it has no idea of like what my voice should be. And I'm just giving some target text. This is again what the model already has. So say I generate. Let's see how long it's going to take. Wow. But basically, what the model is supposed to do is now. Oh wow, it failed. So maybe I should just try again. Yesterday it worked fine. So what it does is basically it uses my voice to generate an audio of that Japanese text. So it's the same accent that I have. I have a very strong Indian accent, of course. So it uses that Indian accent, but it says Japanese words with my voice. So that is the idea. It's clearly not working today. And of course, as all live demos do.
But in this case, the features that are collecting to generate the audio, or no?
You don't know. So
okay.
Even yesterday, what happened is like when I did this, so you see that it's like quite a big Japanese sentence. The first word works well because my own audio is like really, you can hear because it was recorded with the laptop, it's not very clear. So let's see, maybe. So it's catching some words, right? So this is, ideally it would catch the whole thing, but when you listen to this audio, there is a lot of, so it's taking these gaps. Ideally, you want like a full sentence, but you get the gist of it. So this is basically zero-shot transfer. So it's making me say these words that, so I would never be able to say because I don't know the language. And this is like one of those applications. And of course, it's because it's academic, it's free, it's trained on limited data. It's not going to get the best output. But that's like one idea. The other, so this is more along what you would see in like real world. So this is a robot. It's never been trained to walk that way, but it adapts, right? So this sort of adaptation is also in a form zero-shot learning. It has never done this before. It needs to adapt to a new environment. It does so. And yeah, in this case, the model was never trained on those robots as well. So all these are like really cool applications of the idea in general. I don't know why people kick robots, but right, you get the idea, and this is the same company. Again, I don't know why people trouble robots so much, but you see how it reacts to, basically these are like adversarial situations, right? So it has no idea of like what the person's going to do, but adapts to that. Okay, and so just a very quick summary. So what we saw today on a very high level, different ways we can do zero-shot learning. I think I might have tried, if we had more time, to like give a tutorial on the generative part as well. But for now, we only looked at the embedding method. We walked through one example. Yeah, that's it. Should I?
Brilliant. We couldn't hear your demo here, Shreyank, because I believe you didn't share your audio. So can you maybe imitate the Japanese sentence yourself? So you tell us how it sounded?
I think I'll pass that.
All right, questions? Anyone in the room? In person or online?
Coming in person.
All right, you have a question in the chat from Carlos that I believe cannot use the microphone.
I can actually see.
Can you see the chat? I read it out for you.
What if some of the features in the image isn't shown? For example, with the model generate. I would say it would predict, if that part is not seen, it's going to predict 0 for that particular attribute. It's I think in an ideal world, all the images would have that visible, but if it's not, it's just going to say 0. So that's the whole point of having, like, I would say 300 something attributes. So you're not dependent on like 1 or 2, and you're looking at like the larger picture.
I have a question.
Yeah.
If, for example, in Word Today, you have some bias with some words. But with the other methods, how you control that bias? And you are using ResNet, right? How to control that bias? Because you have the feature in the output, but how you could trust that it's not learning from bias.
So so typically what you do is, like, you don't just use the feature as it is, right? So you do some sort of training with it, so that feature is going to adapt. But there is always, and that is a very big problem, there's going to be a bias to the scene classes. So people do come up with ways to like try to overcome that bias, but it's still an open research problem. So I cannot tell you for sure right now that there is no bias.
One question regarding when you showed that you adapted the GAN setup, you showed that the input generator was the attributes. Do you still use noise vector or only the attribute?
We do use a noise vector, and it's also like how, so because GAN training in general is very unstable, so that is also something, like during my PhD, I used to work on like how I choose that noise. Like, should it just be a random distribution, or can I choose that noise in a certain way that my features are going to be better? So that is also something that people do. But generally, it's conditioned on the attributes.
Okay.
That's the only.
So you condition the vector on the attributes?
Yeah.
How it mismatch between the two representations?
That will not be conditioned on the attributes. Right? That depends more on like what you're using as your loss function to adapt there. More questions from people here. This was the whole point. You can also ask Juanjo to test him on how much he knows about his PhD.
I read a paper when they use LLM to extract a description of the image. So then train. So use that features to train more. But I think that how are we trusting that something that we don't know how it works to generate another model?
So we also were working on one paper. I think last year we submitted it, but the idea was then to have like some way of penalizing hallucinations. So you need to like, because I think that's the biggest problem with LLMs right now at this point. And if, of course, it's getting better over time, the number of hallucinations is reducing and so on. But still, like the features, I mean, the descriptions that it generates, there's a lot of junk in it. So we do have a paper on it and like how we can try to reduce it with like different optimizers and so on. But it's again still, I would say, like an open problem. I personally prefer to have, at least at this point, like the data set that I proposed was like a human annotated one. So I still feel like that's better. But of course, for like ease, this is,
Data set like that.
I agree.
And where can I find data set with that labels as a feature?
You mean like the attributes?
Yeah.
So which are the ones that have it? I know Cub has the one that I showed. Yeah, Ava 2 is another, like animals with attributes. Which is the third one? Sun. Yeah, Sun. They also have it's scene understanding.
Yes.
So there's one data set called Sun, SUN. So that's like scenes and stuff. So that also has like some attributes. Those are the three main ones, right?
Shreyank. Shreyank, and today will you show us, let's say, kind of basic zero-shot learning, right? So kind of classical way of doing this. So I was wondering if you could give us a little bit of a hint on what is the best zero-shot image classification method, and what is composed of? What different components? Is it similar to what you explained today, or it's more generative, or what's the best approach at this time?
I would say at this time, especially because of how unfair it is with like clip, and you don't know the overlap in training and test. So I was going to say I can make one or give a presentation of zero diff, but so I would say generative models are definitely better at this point, especially because generalized zero-shot learning is just a harder problem. And so generative models tend to do well in that and in the zero-shot setting as well. So
how realistic is a generative model in a real time?
Not. I think that's a separate problem. Like, how can we optimize the again? Maybe one who can talk about how many hours he spends on like the GPU for zero diff to run, but accuracy wise, which is what we care about at this point, that's still like it uses diffusion models. So you move away from generative networks to like from GANs to diffusion. So that was like the next step to try in zero shot learning. And there's a lot of conditions on it. It's a very complex model that would have taken like this entire 2 hours, I feel, to explain it. But yeah, I think it's more towards that side, because if you're not doing that, generally what people are doing is like vision language matching, which I feel like it's an unfair setting because you don't know what the model has been trained on.
Thank you. Any other questions here in online or in person? Otherwise, maybe I could use your help to really understand something, because I tend to see a lot of article papers, and even in the talks we had earlier, and well, not today, but yesterday, and in this winter school, the idea of zero shot is, people use that terminology quite a lot, but it doesn't feel like it matches with what you explained today, because your zero shot learning, it requires that semantic attributes, those semantic attributes, right? So I was wondering if you could give us a clear way to be able to distinguish between what I believe is zero-shot inference versus zero-shot learning, right? So I think that's probably interesting for many people getting to know the area at the moment.
So I think what I specifically targeted was like image classification. So it's like a very specific task on zero-shot learning. But like you said, what everyone has been saying, people now work more on zero-shot inference. So like I gave those examples of the robot adapting to situations it hasn't seen. That is in a way zero-shot inference. So it's a new environment. It's never done this before. So that's the thing that people report these days, most of the works. But zero-shot learning in general is like, if we want to train any model, it doesn't have to be classification. It can be regression. It can be captioning. It can be like any task. The model has never seen this type of data before. How is it going to do that? Whatever task it is, whatever the downstream task is. So that would be zero-shot learning, because the whole process, you need to like train a model to do something with like some seen data, and you have unseen data. So then the whole pipeline becomes zero-shot learning. But what people do these days is more inference. I don't know if it's like super clear.
It's still a little bit difficult maybe to grasp the actual difference, but I guess it's more like zero-shot inference, simply it predicts something, right? And that's very much it, without really knowing now. And I guess also because we have people working on auto distribution, zero shot, I was wondering if you could try to link the two concepts together, if at all possible, because an unseen class could be seen as something out of the distribution, right?
So people do work on like interconnecting these two things. So like one work that became like really cited was out of distribution detection for generalized zero-shot learning. So the way they separated in generalized zero-shot learning the seen and unseen classes is that they would use an out of distribution detector to tell if the class is coming from seen or unseen. So the model is conditioned. It's a binary classifier, basically, that's going to say, okay, this is unseen. So if it is unseen, then you have a separate model to do unseen class classification. If it's seen, you have a separate model to do seen class. and then you just have to do the harmonic mean in the end, right? So that is like a way in which it is linked. But like you said, in the end, the classes that it hasn't seen is basically you can treat it as out of distribution. But in this example that I gave about birds, are these 50 classes really out of distribution? So they are still like birds, right? So in that sense, it's not a direct overlap of like the two things. I would say it depends on the data set you use for that clear distinction to be there.
Cool. So let's say a company comes to us and say, oh, we want to do this, and it looks very much like zero-shot learning. And it looks very much like this idea of, if I were to have some minimal description of what the unseen classes might be, that would be really great. Or these are the seen classes, these are the unseen classes. How would you go about it? Because that requires some expert knowledge, right, to annotate that. How will you go about it? Will you go with LLMs to answer and give you some information? And how will you do it?
At this point, I would actually search for an expert because I don't trust LLMs personally. But, yeah, I would say that's what I would do. Like ideally, if someone is proposing a project that either that you are an expert or that someone in your university is going to be an expert who can help you with that part. Like I personally would not trust LLMs for at least like a project where it's going to like generate money at this point. So my opinion. But people
some of the data sets, am I wrong in understanding that some of the data sets have created those features, those attributes from Wikipedia and stuff like that?
I mean, I would rather trust Wikipedia over LLMs, yes.
Yeah, you wouldn't trust the LLM to describe a potential class to them. But it's quite common to use a real description and transform that into an embedding, right? Rather than using that kind of attribute that you showed today. Like, yes, it has fur, or it has like a tail or something like that. It's not always like as simple as that, right? Sometimes it is more like an embedding. Cool. Yeah, I feel like I'm talking too much. So if anyone else wants to contribute to the discussion.
There is a question.
How robust are the methods to mislabel data? So if you have trained data that's mislabeled, just break everything.
Can you maybe, Shreyank, repeat the question for
So the question is that if the training data has mislabeled data, how robust is the model to that? So since that mislabeled data is exactly what these things are going to be conditioned on, I would say it's a problem. So it depends on how much of it is mislabeled. If it's a small proportion, then you expect that generalization happens over that, right? So a few mislabeled samples, I think every data set is going to have a few mislabeled samples. So in that situation, it should be fine. But if a majority of it is, I think that's probably going to crash.
Shreyank, I believe that in many data sets, they somehow assume that for the seen classes, you have plenty of images, right? But for the unseen, of course, you don't have any, you have the description. Have you seen anything, and more like, I believe, even more realistic, that would be for seen classes, we have few shots. And for unseen classes, we have nothing at all. How would that work? Is that something you've seen in the literature? Or
I will circle back to the same paper zero diff that I've been talking about that Juanjo is working on.
Okay.
So in that, what we did actually, the motivation for the whole paper was that if we reduce the amount of trained samples, what happens to performance of zero-shot learning models? That was the motivation. So if we reduce from, say, 100% available training data to 50%, 30%, 10%, all models crash, like quite heavily. So that was the motivation for zero diff. And again, zero diff, the idea was then if we have just that 10%, can we use this? I mean, it's a very complex model. There are like multiple different discriminators, there's like diffusion models and stuff. But the idea was that with just that 10%, can we try to reach close to like, say, 100% of the data? Of course, you don't. There is a small margin drop, but in relative comparison to like other models, that performance is not significant, the drop. So still not few shot, but I would say like 10% is like quite low. So in this example that we work with, if it's like 10,000, you're basically working with like 1,000 instead. So it changes a lot.
We could do maybe, how about semi-supervised type of thing? That's something maybe also potentially there, right? There is another question in the chat right now from Carlos, once again, asking about how will you handle imbalanced attributes in the semantic space, let's say.
So I don't know, Carlos, do you mean if like certain classes have like 300 attributes, but then certain other classes have like 50 attributes? Is that the...
There is an example there in the chat, but I'm not sure.
That's what I didn't... How would you handle unbalanced attributes when these attributes are not known?
But the example is there is a lot of mammals, but not so many birds.
So I still don't get it. So does that mean like the number of mammals is more than birds? So the in that particular class distribution is imbalanced. I'm assuming that is the question then. Okay. So the data sets the example I gave with Cub is fine, but like there are data sets where you can do zero-shot learning, for example, on ImageNet, right? So there is going to be a lot of imbalance because it's a lot of different random classes and so on. So I guess as long as we have those manual attributes, and since our models are going to be conditioned on those attributes, I think it should be fine. The imbalance should not be a big problem. But if like say one class has 300 attributes and another class has 50 attributes, then that imbalance I think is a bigger problem.
Well, you need to pre-process the semantic space. Oh, there is one question from Alberto. Alberto, please unmute yourself and go with it.
Hi, Shreyank. How are you?
Good.
I was wondering, do you use for organizing the semantic space, do you use contrastive approaches for the image and stories representations?
So in the one paper that we did recently, yes, it's not always the case. So a lot of time it's just one-to-one mapping without any contrastive learning. But there are like now these days people do use because it does make more sense to use it, right? So people do use it, and of course it is helping when you do use it. With the example.
And if you use it, can it happen that instance by instance the space is well organized, but in general, like globally, the space might be not so well organized?
It could be, but what you would end up, you would see maybe class-wise. So then instead of using like instance by instance, you could do like a prototype of the class and then instance to prototype. So that type of contrastive learning also is possible.
Okay, thank you.
Nice. Any other question? All right then. So if there are any further questions, big clap to Shreyank. Big thank you once again, and also for going there and try to meet people in person. We're gonna take a break until 2 p.m. Where Nacho will be starting his tutorial on transformers. So thank you very much. I'll see you 1 hour and 9 minutes. Thank you. All right. Very good afternoon, everyone. Welcome back. Hope you had a great lunch. For the next hour and a half, we have two talks, right? And the first one comes from our very own Ignacio Nacho Aguilera. He is a postdoc here at the Institute of Data Science and Computational Intelligence and the University of Granada. He did a double degree, I believe, in math and computer science. I'm just speaking out loud from memory, so I don't have anything to read today. So he was trying to detect anomalies, and he went from that to working a lot with transformers as well, for something else, I believe. And today he's going to take us away with some sort of mathematical explanation as to what transformers do and why they work. So whenever you want, you go ahead. Please try to keep it under 1 hour if possible. So we try to stick the two talks in the next hour and a half. Okay.
All right. Yeah, absolutely.
Thank
I'll
you
go
very much.
for 45 minutes.
Fantastic.
All right. Yeah. So it was like Isaac said, I'm working actually with transformers at the moment, and what I mainly use them for is time series forecasting. So in this talk, I'm going to try to explain the architecture, not from the point of a normal class in which I will just list the items of the architecture, but try to give insights from a mathematical perspective of why they do work and why can we stack as many layers as we want. So the index of this talk is going to go from the motivation and mathematical map of transformers architectures. We're going to head to the attention definition and properties to finally describe the whole transformer block and what each piece comes from. Then we're going to talk about the positional encoding and maskings, and we're going to make this parallelism between natural language processing and my own field, which is time series. So I will do this along the whole talk. So I will be talking both for natural language processing and time series, but we will make one section devoted for it. All right, so first of all, I'm going to take 2 slides only just to give a big picture of what transformers are, and we will take these ones again at the end of the talk. A transformer, seen as a black box, is just a stack of blocks and neural network as deep as we want that will have an array X from the domain of n times d as an input. I will provide another sequence as an output. So the main characteristic of transformers is the global token mixing information. That is the ability of, in one single step, mixing the information along the token axis. All right. We will see it later, but in this picture, we can actually see the encoder and decoder of the architecture, the encoder to the left, a decoder to the right, and we will see the differences in a bit. So due to the very good results it has become just the default backbone from sequence to sequence. That is parsing text to text, either going for time series, sound, and also for vision, adapting this problem from vision transformers. All right, so why it became the default? If we have the picture of where we came from, we were actually in the domain of recurrent neural networks, in which we had a very computationally demanding architecture, but very plausible for using it to process sequences. So the biggest gap, of the biggest advantage that this architecture provides is the parallel training. And also the direct access to relate every single token with the rest of the sequence. That is, in one single step, a token I can be related to any J from the input sequence. So why is this important? Because if we make the computation less extensive and more efficient, what we actually obtain is the ability to process larger context and make the architecture wider and deeper. So we can actually use them as more powerful tools. So just to give I don't know if you see the video. it is just a proof that from 2017, where Vaswani and the Google team introduced the architecture, the LLM area has just exploded using mainly this transformer architecture. But we will see at the end of this talk that it is not the only way of going to the moment. So I'm going to tackle this talk and I'm going to divide it in three pieces or three axes. Why transformer work and what do we mean with the assertion that transformers work? We're going to tackle this through the sense of expressiveness. That is, they can represent very complex input-dependent dependencies. The trainability, or the ability to train deep stacks of neural networks, and how we make those gradients do not vanish or explode. And the structural bias, which is the ability to inject explicit information, talking about, for example, positions, causality, locality, inside of the architecture, without relying or hoping that the loss function actually learn and make the weights represent those prior information that we have about the problem. So to get a little bit more mathematical about it, with expressiveness, what we mean is that given an input, which is this array X, we actually obtain a weight graph, a data-dependent weight graph, which is this alpha ij, that will moderate and relate every single token with the current token I. So that is a set of weights greater or equal than 0 that will sum up to 1. And we will see how we perform with this later. But graphically is what we see there. In the phrase, the transformer architecture is great, we will have a relationship, a weight graph relationship of every single token with the one we're considering at the moment. When talking about trainability, and we will discuss it later, what we mean is that we can represent actually the gradient or as the derivative in each of the layers, which is represented by the Jacobian matrix. And if we stack L layers of a deep architecture and we increase this L to be a sufficiently big number, what we are going to obtain is a product of Jacobian matrices, and if they are not controlled, we will multiply numbers very close to 0 and therefore go closer to 0 as we increase the depth of the architecture, or go to the multiplication of very large numbers and therefore explode the gradient. There are two solutions that transformers imply or use to solve this, which are the residual connection and the layer normalization, and we will see them later. Just to give a little bit of an insight, the residual connection will give a clean path for the gradient not to do anything if it doesn't need to. So the layer can actually pass the information forward, and that's it. And with the layer normalization, what we're going to obtain is, after we apply these nonlinear activation functions of the feed-forward neural network, preserve the integrity of the data, preventing them from going to very large vectors or very little ones. Finally, I'm going to present the third axis, which is the controllable structural bias, and we will head to the architecture itself. The controllable structural bias, and we see now the first approximation to the attention function we will have later, is related to these terms B and M included in the formula. So actually, the weights we saw in the combination before, which is the first equation we've got here, the weights alpha ij are just this softmax operation of a set of data-dependent scores, which are the relationships of each of the tokens. B, which is the structural bias, which injects information that we know prior from this problem. And M, that is the mask that will tell the model where it is allowed to see and where it is not. Before going any further, I want to say that this talk really gets into the right moment, because we are talking a lot in this winter school about these large architectures, and it is a good idea to know the principles and know the basis before we head to them. So in large language processing or natural language processing, what we got as an input is just text, which is parsed by tokenization and several techniques into a discrete ID or discrete value array or vector. In time series, we've got this vector already, but the difference is that these variables are mapped into a continuous domain. But at the end of the day, what we have for the architecture is a vector of the real number domain of dimension n times d, with n being the number of tokens and d the model dimension or the feature size. And we will use the architecture for both of the inputs. So it's just a black box for us to the moment, but able to insert text and time series both. So to provide a little bit of insight, we all know what the token in natural language processing is. We've got several choices: character division, word division, word piece division, whatever we want to. And in time series, we've got mainly two options. Time steps, that is considering every single time step as one token, or patching, that is slicing the time series to provide a small time window as an input to the architecture. It is critical, this decision, and we will see it at the end. All right, so what I was saying, same backbone, but we are going to turn 3 knobs to configure the architecture for each of the type of data. This structure, that is using masks and biases related to the type of data we are using, for example, locality or causality or periodicity in time series. Positional encoding, we will see later that the classical positional encoding is sign and consign based, but that will not be the best option in every single problem, time series, for example. Third, the output head, which will define which task are we trying to tackle. That will be next token classification, forecasting, autoregressive, whatever. All right, so we are just about to start the definition of attention, but I would like to compare where we were before transformers and how they manage the information. So a clean way to compare recurrent neural networks and convolutional neural networks with transformers is what is so-called the path length. That is the minimum number of positions or of time steps that information needs to travel from position J to influence the current token A. That is, in recurrent neural networks, for example, imagine that we want to relate a time step which is separated from J 30 time steps. We will need at least 30 hidden states. We all remember this architecture of recurrent neural networks in which just pass these hidden states as messages, trying to process these inputs sequentially. So we will need at least 30 hidden states, or what is the same, the difference from J to I. In convolutions, if we fix the kernel size with K, we will need to stack at least L layers such that the inequality K multiplied by L is more or less greater than equal than this subtraction of indexes. That said, for example, in the example of 30 time steps, what we will say is if we fix the kernel size with 3, we will need at least 10 layers to relate J with I. And it is very important to note that we will also relate every single token in between, so we will dilute a lot the information. In transformers, this does not work like so. If both positions are inside the input sequence, that will be a O of 1 complexity that will be made in one single layer. All right, so now we've got everything we need to head to the definition of attention. So we are going to make this very progressive and try to get into the details. So attention, we all know, is just try to learn 3 views of the same input, and that's what we call Q, K, and V. It is very important to note that these projections are learned separately, so each of them will have their own sets of weights. And the intuition behind them is that Q is what each position is looking for, K is how each position is going to be matched, and V is which content each position provides. These projections are part of the formula we're going to see here, but we are going to make it progressive, as I said. So the first part and the most important part of the attention is the pairwise similarity scores. So that is, given the projections that we are learning, we are going to see how Qi and Kj are related. Just to remember, the scale dot product or the dot product of Qi and Kj are just the modulus of each of the vectors multiplied by the cosine of the angle that they do form. That is like saying how close are those vectors in their own space. A little detail we're having here is that we are scaling by the root square of the dimension of the keys, and that is very important. We will say later why. Then, after we've got these pairwise similarity scores, we apply the softmax operation. Just to remember the softmax operation, we'll see the formula in a bit, but it was related with the exponentials and had the property that if we apply it row-wise, as we are doing here, what we obtain is that for each of the positions of the row, we are going to have positive values, and they will sum up to 1. So we can actually interpret those values as a probability distribution. And finally, we've got what we call the addressing, which is how these softmax scores apply to V to generate the output. So that said, we've got the formula already completed, and we can see the picture again. So now we know what attention is. We're not distinguishing between the two types of attention that are present in transformers, because we all know that the architecture has both self-attention and cross-attention. For example, here in the encoding, we've got self-attention in which X, the input, is exactly the same. But in the decoder, that is not the case. And we will have different input for this multi-head attention. We are not talking either to the notion of multi-head attention yet, and we will see it later. All right. So I know there are several talks that will tackle this topic on Monday, I believe. It's very interesting, the kernel view of the attention. We will see in those talks that we can actually simplify or see these neural networks as kernel smoothers, and that is exactly what happens with the attention. A kernel smoother has just the formula that we see here, in which we have a W function that relates or gives the weights, and the kernel function inside those ones. If we see it, is just we could see that it is just the relation between the input and every single other token divided to the sum of these weights or importance. So we're just normalizing it. All right, so attention has the same structure, being our kernel function related to the exponential of the dot product. Why the exponential? Because we're using the softmax operation. So it is directly proportional to this exponential of the dot product scaled up by the dimension of the keys. And we saw here that is the softmax operation, which has, of course, the same properties of the same appearance as this kernel function we were talking about. All right, so seeing it position by position, what we have is exactly the function that I said, in which this k that we talked about, this function from the kernel, is the exponential of the dot product. And it is just an average of the values mapped to this V representation we learned. So you can actually read attention as a soft retrievals, in which I'm saying which past tokens do I need to consult in order to make or to provide the output. Why is this useful from the mathematical point of view and also from the practical point of view? It demystifies attention, so it's just a function that we actually know, but represented in a matricial form, which is very typical, of course, in kernel learning. We are explaining how each position is related to each other, but not in a distant fashion. So we are not talking about how close in terms of space is each point to every single one, but from the notion of similarity. And it also gives a handle for the scalability, because seeing this kernel matrix, we can actually use, for example, sparse techniques to make this computation more efficient and try to avoid calculating and computing the attentions that are not needed and not important. And it also clarifies the role. I've used these both words before in these slides: content aggregation and addressing. That is relationship and the output of the attention. All right, so we've got the attention definition now. So that is related. I'm going to make this connection with the expressiveness axis that I talked before. And in time series, it can actually be seen very good if we use this patching tokenization that I talked at the beginning. What we are saying is, if we're considering this orange patch, we try to get high weights for those patches or those tokens that are very similar in these terms of similarity via this cosine aggregation and of the input sequence. All right, so let's head now to the trainability axis. Now, somebody can ask, if the dot product is what gives the relationship of Ki with Qi with Kj, why are we dividing it by this square root of the dimension of the keys? Now, if we assume that Qi and Kj are just independent and they have zero mean, which is typical because we are going to use layer normalization, so we can actually assume this, and they've got variance sigma squared, what we obtain is that the variance of these unscaled logits is directly proportional to the dimension of the keys multiplied to sigma to the fourth. Layer normalization will control this sigma, and we will see it. But what we cannot control, or what we do not have under control here, is the dimension of the keys. So what this means practically is that if we make this structure really wide, not deep, but wide in terms of the dimension of the keys, we are going to increase the variance of the logits. And that is very important, and that is a very critical part of this attention mechanism. What happens if we do not scale the logits and the variance increase? If one logit dominates because of how the softmax operation is performed, it is going to have probability 1 or close to 1, and the rest are going to go to 0. So we are going to have a very peaky softmax. For example, in the two-class case, we can actually define the probability 1, which is related to the first logit, and the probability 2, which is related to the second logit. Just by doing the calculation, we divide both the numerator and the denominator, and both parts of the fraction, we will divide it by the exponential of Z1, and we can obtain this probability 1 as a sigmoid-related value. Why am I doing so? Because I can actually do the derivative by the properties of the sigmoid, and if the probability 1, therefore this 1, is very close to 0, we can consider it very close to 1, I mean, very close to 1, we can consider it 1, we will have 1 multiplied by 1 minus 1, that will be 0. So the gradient and the derivative for the point, that will be very close to 0. So we are not able to learn, or we can learn very little. So now that being said, this scaling up the logits make us provide wider architectures and being able to create more features or learn more features. All right. So I talked about previously that we have two types of attention, self-attention and cross-attention. We said that self-attention is the attention mechanism that has three vectors x at the same input, which are the same vector. So it's the input of the sequence. But in cross-attention, we will have two types of inputs. The ones derived from the encoder, which are related to K and V, and the ones that we are trying to build from the decoder. That is XTGT we've noted here. So we've got this one, which is what we have made to the moment or till the moment in the decoder, and this, the output of the encoder. So the intuition behind this is that self-attention is going to try to learn features within the same sequence, whereas the cross-attention is going to try to create this output sequence while learning from the encoder output. And we saw it when we were talking about here. We saw that this come from the output of the encoder. All right. So now we've got mainly or mostly or the picture about attention. Now we know what attention is, we know what self-attention is, we know what cross-attention is, and we know why we are scaling up the logits. So what is the price of attention? Because we talked about the advantages considering recurrent neural networks, but the main drawback of this architecture is the multiplication of Q and K transposed, which leads to both time and memory complexity related to n squared. So there are lots of proposals towards mitigating this issue. But for example, the token choice that we talked about in time series, in which we could have either time steps or patches, is very critical because that will effectively reduce the dimension n. All right, so now that we know mostly everything we need to know, let's head to the transformer block and give the whole perspective of it. So one single detail that we are not talking about, you've seen that attention is not mentioned in the architecture itself, but multi-head attention. What we've seen to the moment is how each of the heads of a multi-head attention behaves. That is, we are going to repeat this architecture h times, so as many heads as we want, and learn these representations Q, K, and V separately in each of those heads. Afterwards, what we are going to do is just concatenate them to create one single vector or array and learn a representation, a way to project or combine the information from those heads. So really, what we are going to do is learning different geometries. And this is very important because it's very, very dependent of the topic or the type of data and the type of problem we are facing. In time series, for example, this could actually learn plenty of things. For example, yesterday, I think it was Ivan that talked or made a question about transformers and chess. So for example, when dealing with chess and trying to predict the best movement for the next position or for the current board that we are playing, we find that these heads, for example, could be devoted to how to learn how which of the pieces of the chess game moves. So one could be devoted, for example, for learning how a pawn moves, king, tower, horse, whatever. In time series, this is very typical, and it can actually, well, you could actually make it learn wherever you want, but it's very typical to say that transformers for time series can learn, for example, to represent each of the single-valued time series of a multivariable time series in each of the heads, or patterns such as locality, periodicity, global regimes, seasonality, trend decompositions, and so on. All right, so I'm going to let's move to the next block of this, the feed-forward neural network. So now let's review a little bit what I said early on this presentation. The attention mechanism is devoted to mix the information within the token dimension. That is, relating every single part of the input with every other them. But we are not mixing the information across the channels. So we are not mixing the information across the characteristics or features. That is where feed-forward neural networks are applied into transformer architecture. And they are very simple, but they also provide the nonlinearity that we need to create richer features for the architecture with this sigma function, which is the activation function. So we typically try to make this feed-forward neural network much larger than the dimension of the model. Why? Because we want to enrich the feature space and the combination space in order to encapsulate it and make it all fit in the model dimension. All right. So now, of course, this feed-forward neural network is related to the expressiveness axis that we were talking about before. And some people, some authors can say, and it is also correct, that this feed-forward neural network is actually applying a one-by-one convolution across the dimension of the features of the channel or the channels. So I just wanted to mention it, so if somebody reads it, that it doesn't sound weird. All right. So we're going to move now to two key things that are residual connections and the layer normalization, which are going to help us make this architecture as deep as we want and still converge. So residual connection was presented with the ResNet architecture, and it is a very simple idea. We are going to learn a function with our neural network. That could be this f function, and we're going to add the same input to the learned representation. So that is, we will add x, which is the input, to the transform value of the neural network. This is applied in transformers in two ways or in two phases. First, with the multi-head attention, and second, with the feed-forward neural network. We've got, it is key for us because it will help us in two ways. First of all, it will make the neural network be able to not make great changes, so it can actually use the input, which is already a good baseline, and make very little progress and increases to this input x to modify to the output and learn from it. And it will also give us what I was talking about previously about this clean path of the gradient. As we have there the identity, when we make the derivative, we're going to have the identity there. So the Jacobian of f could be 0 or close to 0 if we don't want or we don't need this layer to learn a thing. So for many layers, this is going to give us the stability that we need to train deep stacks. All right, so on the other hand, we are now controlling the gradients, but not the values. And it is very important to control also the values output from the architecture. For that purpose, we use layer normalization. Layer normalization is very simple. It's just providing zero mean, unit deviation, standard deviation output from the feed-forward neural network and from the transformer block. So why do we want to do so? Because layer normalization is going to make us make the activation safer, because if we see the activation graphs, for example, for a ReLU or whatever, we see that it's going to explode with big values or tend to 0 or to extreme values on the on both ends or both sides of the function. It is also going to improve the gradient stability because we're going to control this among many layers. So we are going to control these values in order to be able to differentiate the whole structure. And it would also make the initialization a lesser problem or less fragile for the initialization, as if we initialize the architecture with very little values, those are going to be normalized and scaled. So there are two ways to apply this. What it's called the post-layer normalization, which was the originally provided in the transformer architecture, and is applying the layer normalization after the residual, or applying the layer normalization before the function itself, which is the pre-layer normalization, which is what we do actually with current architectures. All right, so let's see the whole picture. Now, just to give a little bit of overview what we have seen. We've seen that we can actually have expressiveness. We've seen all the components of the transformer block we're going to review now. And we've seen that we can actually train in a stable fashion, both wide and deep architectures. So the transformer block goes like so. It's going to normalize first, apply the layer normalization to the input, then apply the multi-head attention, and add the residual. And in the second phase, is going to apply again the layer normalization, the feed-forward neural network to obtain the nonlinear features, and again add the residual. So we can actually see this in every single position of this transformer architecture. Multi-head attention, normalization, and residual connection, feed-forward, residual connection, normalization, and repeat it all again. So with everything said, what are we missing to this moment? We're missing order and causality. And we're going to go to a very interesting property of attention as we have seen it to the moment. So, key fact. Attention is permutation equivariance in self-attention. So what this means is if we make a permutation over the input, the attention is not going to differ. So the attention of the permutation of X is the permutated attention of X. So attention is invariant to this permutation. Let's give a little bit of a sketch of proof that is very, very simple. That's why I included it in slides, but let's have a review of it. So we can define the permutated input as X prime, which is just multiplication of a permutation matrix with the inputs, and we can define along the three learned representations with the permutation. That is Q prime, K prime, and V prime. So with that being said, we can actually compute the attention scores, which are going to be the permutation matrix to the original, multiplied to the original scores and multiplied to the transpose of this permutation matrix. Let's keep on with the argument. So now we've got the scores, we need to apply this softmax operation. But the softmax operation, we're going to apply it row-wise. And it is invariant to this row-wise permutation, where we are going to obtain is exactly the same vector, but with the positions turned around. So we can actually say that A prime is just P multiplied to A multiplied to P transposed. So finally, we've got the attention of X prime, which can be computed as the result of the softmax operation multiplied to V prime. And we've got the property that the transpose of a permutation matrix is also the inverse. And therefore, this is the identity. And we've got P multiplied to A multiplied to V. That is P multiplied to the attention of X. That is very, very simple. But what we've obtained is that attention itself does not encode order. So what this means is that if I inject into this architecture AB or BA, the attention scores are going to be indistinguishable. And that is also very important, for example, with natural language processing. That will mean that if I provide a book of 100 pages, it will not matter if we are reading first page 40 or for page number 1. And also for time series. Both time series you are seeing in the slide are the same values, but they are just shuffled in time, and therefore we've lost all the relation of in the data or in the time axis. So to solve this problem in the original transformer, they included this position and encoding based in sine and cosines. And the intuition behind this, well, what we are going to apply is to even positions the sine operation, to odd positions the cosine operation, and we're going to obtain a frequency relation of each of the tokens with the rest. So we can actually use high frequency to make short-term locality or wider patterns or frequencies to relate longer sequences. I'm not going to stop really on this, but there's one important property of this positional encoding operation, that is that if we shift it a long time, it's just multiplying a rotation matrix to the original positional encoding we had. All right, so last item we've got left, masks. We've got the last part of the structural bias, which are masks. Masks are just an additive item to these attention scores, which are either 0 if we want to consider this position, or -infinity or a very large negative number if this square is not allowed. What it is going to make effectively is that the softmax operation is going to inject or provide 0 probability or close to 0 probability in places where -infinity is, and preserve the probability where 0 is. So there are very a wide range of masks that are applied. For example, this causal autoregressive mask, in which only the past positions are allowed to be seen, or bidirectional masks that are very useful, for example, for encoding, decoding, or in painting. And also the padding masks, in which if we need to make a padding of the input for that hygiene, we are going to tell the attention not to look to these padded positions. All right, so this is just a visualization of it, but what it provides or what it enables is that the model sees only the information that they should or they need to be considered. So it is important that we do not make, for example, a forecasting neural network and make it see the future, because that will be like cheating. All right, so now we are going to head to the last part of the talk, in which I'm going to make a relationship between language and time series. We've seen it along the slides. So, but really the difference between language and time series is focused on the token definition, the output head, how we are going to deal with each of the variables, and the attention, or the attention mechanism itself, which is dependent of the data. And typically in time series, we are not using the vanilla transformer or vanilla architecture with this self-attention. So we've said that the tokenization is a very, very important design knob, as we actually define the dimension n. So either choosing patching or this data element view with the time steps is critical to the architecture. We are going to provide more information or low grain information if we go to the time step sites, or a higher level could be said of information if we go to the patching tokens. So also the output head is very intuitive, that we need to tackle and tune this layer. We can actually use it, for example, for anomaly detection, as Isaac said before, that it was part of my thesis, or to forecast the next time steps, or in an autoregressive manner. So exogenous and variables and calendar embeddings are also very important, because in time series the main difference between natural language processing and time series is that we've got a continuous domain, and we've got also these exogenous variables that are from the environment where the sensors or where the time series are being measured. So we've got, for example, temperature, humidity, and so on, which is very related to the problem. It could give us insights of the system itself and provide a way to normalize the knowledge that we have with the ambient conditions. All right, so I wanted to keep this talk very encapsulated, just to give this view of transformers. So I'm going to review very lightly what we saw, but we saw that transformers are able to create or be expressive by mixing the information both with the attention in the token embedding and the token dimension, but with the feed-forward neural network in the channel of feature dimension, create with them nonlinear values, and provide this whole expressiveness. In the part of trainability, we are able to make these wide and deep architectures and still have the gradients to converge and the values within a normal or great range to work with them. Also related with the multi-head attention, in which we're going to make this even or go further with this idea and combine several representations. And with the masks biases, what we inject is this data-dependent, task-dependent information we know priorly from the input. So there are plenty of things left to do in this area, and we all can see, and we will see it better when this winter school finishes and we look behind to what we've seen in the talks. But transformers are the state of the art in most problems. But the main question is attention the only way? And we are seeing with state space models, for example, such as Mamba, that there are some alternatives growing in there. We've also talked about this architecture from the side of inference in one single step, but now we're moving towards chain of thoughts and feeding again the architecture and decomposing the problems in several to-do list items. In time series, it's very important the correct adaptation of these kind of architectures, because it's not non-trivial, and there are some issues that are still left to adapt, as for example, some people are working here. For example, myself and Christian just published a recent paper about this positional encoding in time series for transformers. And the whole, for example, the causal circuits and the interpretability and explainability of this model is also being tackled, as well as the efficiency, limited data scenarios, noisy data, and of course the foundation models to provide a solution, as we saw yesterday with the tabular data sets in the talk. So that will be it. So thank you all for attending to this conference, and I'll be pleased to answer your questions.
Thank you very much, Nacho. All right, we've got 3 questions already in the chat, and the first one I think I need to read it myself, so I will go with it. So Carlos is wondering if what you think. So do you think the transformer architecture can be simplified from a mathematical perspective in LLMs at scale?
It is a very interesting question. I mean, I don't know if simplified in a mathematical way. Of course, yeah, we talked about in this. I talked about the kernel vision and these sparse attention mechanisms. The straightforward optimization of this architecture is to see whether every single attention is relevant or not, and try not to compute irrelevant attention scores. For example, myself, I'm working in the last revision of an article devoted to this in time series, in which we use the locality notion of a time series in order not to compute anything that is far away from the diagonal of the attention scores matrix. So we simplify the attention from n squared to logarithmic, which is an important upgrade.
All right. So maybe following up from there, I was wondering if you think that for some other problems, do we need such a monster? Because when I think of transformers, I feel like they are really big, right? And you have to basically do an entire talk to try to explain to us why they work, while we might not need such a big monster for many things that we do on our daily basis. But what's your view on that?
Yeah, that's a very, very good question. And I will pass all these slides for you because I placed some bibliography at the end of the slides. And there is one particular one which really tackles what you are saying, which is... No, I think I didn't put it. I will pass it on the group later. But there is a very good work, which is really, I think the title is something like "Are Transformers Effective for Time Series" or so. And the paper is pretty beautiful because what it does is it takes architectures that have millions of parameters and hundreds of millions of parameters and place it against a linear architecture. And the linear architecture just outperforms all of them in the chosen data sets. So what they are trying to say is try to focus or try to discover the problem where this architecture is the only option, because if not, it would be better to use lightweight approximations and lightweight solutions.
Great.
So yeah,
Thank you.
of course.
Fantastic. Thank you, Nacho. Maria Victoria, you have a question. You can go for it if you want to. I don't know if you can hear me. Hopefully, yes. Oh, you're still muted.
Yes. So if you like, Isaac, you can read the question for me. But anyway, the question is that if you know a theory purely mathematic, addressed to mathematics, that be satisfactory for you in order to explain the transformers. So how is the development of the mathematical foundation of transformers, basically?
So from a mathematical point of view, trying to get the approximation or the whole definition of attention or the whole definition of the transformer architecture, because that will be just a composition of functions, but we interpret it in a matricial way just to simplify and to get into the calculations. So just to get...
Is until what extent the theory have a very strong mathematical substrate supporting this?
All right, now I get. Yeah, I mean, somebody could say, I think there are only two ways of seeing this. After I presented the whole monster of attention and having this, I think it was this slide. Yeah, here in the transformer block where I present at the end, this one. I present the whole monster as a composition of functions. There are two ways of seeing this. First, somebody calculated everything very well, just not to miss any single spot, and have the theory behind, even though I have not presented it. Or you could actually see it as we've faced several problems when dealing with this architecture, and we tried to patch it error by error when we faced it. And I think this second approach is much more fixed to the truth. I mean, probably the layer normalization or the fit for one neural network and all the multi-head attention were all just refinements of a prior idea that was developed, was found to be non-sufficient or have issues, and then incorporated. So going to the question, I don't think there is a whole holistic mathematical view of this architecture, because I think it's more a engineering type of work in which there are several issues and try to cover them.
Thank you very much. So the mathematical approach will came in the close future, I expect.
Yeah, I hope so as well.
Some part in the war. Hopefully Granada, who knows?
Who knows? All right, last question, please, from Alberto, if you don't mind unmuting yourself.
Hi, Nacho. Hello.
Hi.
Thanks for the talk. It was very insightful, very good. I wanted to ask you about patching in time series. As you said, the size of the patch is a critical choice, definitely. And at what extent do you think that you can make a transformer for forecasting in time series, for example, work if you use a fixed patch size? Because as I see it, time series, the information and the local information can vary a little bit all along the time axis. So what's your view in this matter?
Yeah, that's a very, very good question. I'm going to head to this patching that we were talking about, for example, here. I mean, I critically chose here the patch size to match the input pattern, as you've seen. So for academia purposes, that will be very clear because you can actually see that both of them are related. But it is directly related with what you are talking about. If you fix the size of these patches, which I believe I've placed, I hope I didn't skip this one. I think this one, yeah. The paper that is cited there is called Patch TST, and it's a neural network for time series based on transformers devoted to this patching architecture with fixed patches of size 64. So what I found reading the paper is that as you fix the patching size, you shall not or you may not capture all the patterns that you want. So what happens if there is a pattern that takes 100 points to appear and not 61, 64? So that will be critical because that doesn't mean that you're not going to see the whole pattern, because you will, because there will be at least 2-3 patches that encapsulate it, but you will miss the local information of seeing those patches relative in time one by another. So I've seen also approaches in which these patches are overlapping. So you will try to miss little information in terms of locality, but of course you're going again into increasing the end dimension and therefore reducing efficiency. So that is important. And I've seen also very interesting transformer architectures which are related to, for example, season trend and the composition transformers that try to encapsulate this token notion or this whole time series notion in the form of attention heads devoted to this. So I think this is critical. And I have not seen, so as we say always, to the best of my knowledge, I don't know any architecture that learns how to pick those patches. That would be very interesting because you can actually do things like seeing where the derivative of the time series change. So you can actually analyze the slope, for example, and doing tricks like so.
Yeah, or maybe even working in the representation space, in the embedding space. If you are cutting because of the fixed size, if you are cutting a long pattern, maybe you can work in the embedding space. So to get close these two patches or these end patches that form a pattern. Maybe that's another alternative.
Yeah, but it will still be critical the size of the patches that you try to obtain, as if you don't encapsulate the whole data or as much data is needed to understand this pattern, you will not be able to learn it.
Yeah, exactly. Okay, thank you, Nacho. Thank you.
Great, thank you very much. I'm afraid we don't have time for more questions here, but hopefully this evening we will have more time if you want to. So thank you very much once again, Nacho, for your talk. Big clap, and you can react if you want in the chat. Everybody is doing it. Next up is Han-Jia. If you could please show your face and start sharing your screen, that'd be fantastic. I do not see you yet. But I'm.
Hi, Isaac.
There
Can
you
you see
go.
the screen?
Yes, we see it. We hear you. So, we're gonna crack on with this. So, let me all introduce you to Professor Han-Jia Ye. I hope I pronounced it correctly. He is an associate professor at Nanjing University and a key member of the renowned Lambda group, where he has built an incredibly prolific career in representation learning. With over 80 papers and a research focus on how to reuse pre-trained models, his work really aligns well with what we're doing here in this school on general purpose AI. Beyond the research, he is really active as well in many different peer-thing activities, and he's an associate editor of of FAMI and other conferences like NewDips and ICML. So once again, he might be one of your reviewers at some point, or the editor of your work if you aim for that such a high conference or journal. So without further delay, once again, thank you very much for joining us. And whenever you want, the floor is yours. Thank you.
Thank you, Isaac. Hello, everyone. I'm Han-Jia from Nanjing University. Very glad to have this talk in general purpose AI system inter-school. The title of this talk is Learning to Reuse Pre-trained Foundation Models. Let me start. Machine learning has revolutionized the way we solve real-world AI problems in various fields, for example, in image recognition and detection via language understanding. In the machine learning paradigm, the whole paradigm is very simple. We first collect data. From various fields, and we apply machine learning algorithms. And finally, we obtain the machine learning model. This is a task, and we use machine learning algorithms, and finally obtain the model. In the classical learning paradigm, we use some objective function, and we optimize the model parameters from scratch. For example, we use gradient-based optimizer and update the model parameters. In this case, we find we need to carefully determine which data to use, the model architecture, the training objective, and the inference strategies. All these terms will influence the ability of the machine learning model. Here, let's focus on the final part, the output machine learning model. And as we can see that we can apply machine learning algorithm in a lot of fields. After we learn a model, and then we have a pre-trained model, that is a machine learning model, usually well trained based on a certain data set. The model could be a linear model or a neural network or the language model, large language models. And since we have already trained the model in a particular domain or particular task, a data set, we think the pre-trained models may encapsulate value inductive bias, which could be beneficial for downstream tasks. Since we learn the model from different fields, the model may capture some kind of the useful information, the kind of knowledge from a particular domain. So if we have a lot of machine learning models, pre-trained models, then we may extract some knowledge from them. As we can see, there are a lot of machine learning model platforms such as Hugging Face and different similar to the trend of the size of data sets, the number of data sets in the publicly available. We can see that in those platforms, the number of pre-trained models also increased a lot across years. There are more than 1.3 million pre-trained models from the platform. And the pre-trained models could cover a lot of types. For example, the multi-modal models, the vision language models, tabular models, and different models. So let's review the machine learning paradigm. We can see in the first stage, the whole paradigm is model-centric, which means we try to improve the performance of the model by changing the model architecture. For example, we design the model architecture by incorporating the inductive bias from a certain domain. And then we consider the data-centric paradigm. The data-centric means we do not focus on the design of the architecture, but we collect a lot of data. If we have enough data, then we can improve the performance of model. But now, since we have a lot of pre-trained model resources, maybe we can have another way to improve the whole ability of the machine learning model. So the next step could be we change from learning from data, the data-centric way, to the learning from both data and pre-trained models. That is maybe the pre-trained model-centric. So our main talk of this talk is to consider incorporate the pre-trained model resources, then the whole machine learning workflow. We name it as a model reuse. Let's reuse pre-trained models. That means we try to consider how to take advantage of the pre-trained model resources that may capture a lot of expert knowledge inductive bias from different domains in our target machine learning task. And we expect by reusing the pre-trained models, we may achieve the expert level ability, and we may reduce the number of training data, and we may avoid forgetting to some extent. But how could we reuse the machine learning models effectively? There are two major ways. The first is reuse a single pre-trained model. For example, there are a lot of pre-trained models on from different huge data sets for vision and language tasks. We can fine-tune the model, or we can distill the knowledge from those models. However, since we have some machine learning pre-trained model platforms, we may consider change. We may switch the way we reuse models from reusing a single model to reuse the model zoo. That means we reuse multiple models. We may combine those models together by some merging techniques, and we may also select one or more pre-trained models from the model zoo. So in this way, the learning objective becomes given a fixed set of pre-trained models. There are 1, 2, 3 to m models, and we need to design a model reuse algorithm A prime that we take advantage of the pre-trained model zoo as well as a target task to improve the ability of the final model. And in this way, we want to improve the ability of the model and decrease some burden, a lot of different burdens and other things. So by building on existing models, model reuse may accelerate training, lower the computational and data costs, and mitigate catastrophic forgetting to some extent. So how could we reuse a model zoo? Let's consider how we solve some real-world tasks. if we for example, in university, if we have a programming task, a programming homework, how to solve it. Maybe we may first search some materials from the internet or from the library. We search some most relevant solutions for this task. However, the solutions online may not be the same as our target task. So after getting similar solutions, we need to adapt this solution to some extent based on our task. So similarly, we can view these two steps as the pre-trained model selection and pre-trained model adaptation. So we think this may be two important steps in pre-trained model reuse. So given a model zoo, and for task 1, we may first select the most relevant model, the most suitable pre-trained model from the model zoo for task 1. And then we adapt the selected green model based on the data from task 1. And for task 2, we also take advantage of the model zoo. We select another model, the pink one, and we adapt it based on the data set from task 2. This is the two steps of model reuse, the pre-trained model selection and the pre-trained model adaptation. The model reuse notion originated from the learnware notion proposed by Professor Zhou Zhou in 2016. I think he will introduce the learnware notion maybe tomorrow. If we can take advantage of the pre-trained models in this way, why we can obtain better performance? This is a basic intuition, one of the intuition. As the machine learning development develops, originally we use a single method for a task. We can learn a decision tree or SVM for a task. And how could we improve the ability of the model? We can consider ensemble or selective ensemble, means we train multiple basic learners for a certain task. And then we combine their performance, a part of their performance together to improve the final ability of the model. So in this way, we use multiple basic learners. And we can see that machine learning evolves in circles. At first, we apply a single model, and then we use selective ensembles. And now, we may develop a stronger next generation model, maybe the deep neural network. And then how to improve deep neural network? We may combine their abilities together based on some pre-trained deep neural network models. And in the next step, we develop the language models, large language models. And how could we further improve the ability of the foundation models before the next generation machine learning model? One possible solution is we can take advantage of the whole of the multiple of the pre-trained models. So as we can see, the machine learning evolves in circles, and model reuse can be seen as an efficient and a structured form of ensembling existing models to extend the capabilities without retraining from scratch. Since we have the models, they capture a lot of the domain knowledge and other things. So reusing the pre-trained models could be a way we improve the ability of the machine learning paradigm. Let's focus on the two steps in a pre-trained model reuse. The first is the pre-trained model selection. The input is a new task with limited data. For example, target task. No matter it could be the vision task, language task, or tabular task. And we have the model zoo, the pre-trained models. For example, here are 4 pre-trained models. And how could we select the most suitable model? Because the suitable is very ambiguous. So we can pick a pre-trained model from the model zoo to maximize its downstream performance under some constraints. For example, if we pick, for the 3 models, if we can obtain its fine-tuned performance on the target task, we can then use the fine-tuned performance as a kind of the metric to select one of the pre-trained model. For example, the second green pre-trained model, its fine-tuned performance is 93, the highest one. So this pre-trained model may be the most suitable one for the first task. and we can do this multiple times for each of the tasks. So this means the pre-trained model selection step. We select the suitable pre-trained models for each target task from the model zoo. And as we can see, the fine-tune incur a lot of computational burdens, and it may require a lot of data to fine-tune the pre-trained model. So it may not be an effective way to select pre-trained models. And the next step is the pre-trained model adaptation. Given for example, there are several target tasks, and given the selected pre-trained models, and we can fine-tune or we can use some advanced adaptation strategies to adapt the selected model to the target task for each of them. And as we can see, the adaptation has been investigated across various domains: the tabular domain, image domain, visual domain, textual domain, and also across various tasks. For example, in zero-shot, future learning, and continual learning, and other advanced tasks. So, we can see that select the in the whole model reuse process, we need to select the most suitable pre-trained models at first, and then we apply the adaptation scheme to improve the joint performance. So the two tasks or the two steps are coupled. And since there are a lot of advanced adaptation strategies, in this talk, we will mainly focus on the pre-trained model selection step. And let's see the vanilla strategy to select the pre-trained model. The vanilla strategy is to try to approximate the fine-tune performance for each of the for the target task based on each of the pre-trained model. How could we fine-tune? We need to optimize some objective on the target task based on the data. And we apply multiple forward and backward passes over each pre-trained model. For each pre-trained model. And in the vanilla strategy, we can see if we want to select among M pre-trained models, for one task, it requires M forward and backward passes. So it incurs very high computational burden. And how to increase the efficiency? The one improved strategy is to transform the forward and backward strategy to the forward-only strategy. For example, if we have a target task, the data set from the target domain, we can try to extract features. For example, if this is an image recognition task, we can take advantage of a lot of the vision recognition models to extract features for each instance from the task, each image from the task. And we can extract features. And then we can design some criteria to evaluate the quality of the feature extracted based on the pre-trained model. For example, if the extract feature is based on the representation space or the embedding space, if the same class instances are close to each other, and these different class instances are far away, and then we can treat this feature space as an effective feature space. So the improved strategies such as LEAP, LogMe, and GBC, they design a lot of the criteria to evaluate the quality of the features or the logics. And in this way, although we reduce the we remove the steps to do backward passes, however, the forward passes also incur a lot of computational burden when the model zoo is very large, since we need to do a forward passing for each of the model in the model zoo. So our main motivation to improve the pre-trained model selection is how to select pre-trained models efficiently when the model zoo is very large. So our main idea is to transform this task as a learning-based task. So based on the results of, since there are a lot of pre-trained models, once we release a pre-trained model, we may also release its results on some public data sets. For example, the ResNet or the CLIP or some language models. They all have benchmarks, some public benchmarks, and or the leaderboard, and we can obtain their results, their ability on different instances from the leaderboard or from some benchmarks. And we want to learn a predictor to estimate the ability of the pre-trained model on some unseen tasks. For example, the left are the pre-trained models, the results on some existing historical tasks, although they are maybe sparse. and we want to generalize the select of the model, the selector to the unseen tasks, the right side. So how could we do this? Our main idea is to construct kind of the meta representation. Originally, the representation learning learns the representation based on for a particular instance. However, now we need to learn the representation for a set of instances, that is a data set, or a model, a pre-trained model. So how could we construct the meta representation? If we can assign a vector-based representation for each of the pre-trained model, and if we could also transform or represent a data set, for example, with limited instances, into a vector, and then we can transform the pre-trained model selection task into a representation learning task or a similarity mirror task in the model task space based on the meta representation. So when we want to select the pre-trained models, we only need to calculate the vector-based similarities. So this could be very fast if we pre-calculate the meta representations for all the pre-trained models. So our main idea is that we learn a way to construct the meta representations from historical interactions between pre-trained models and seen tasks. And then after the learned selector, we expect it could be generalized to unseen tasks and even to unseen pre-trained models. And how could we construct the meta representations? For the representation of the models, we assign a vector, for example, a d-dimension vector, one for each of the pre-trained models, and we want to learn such kind of the representations in a supervised manner. We will mention the way later. And for the task representations, for example, we use the classification task or the image recognition task as an example. For each of the classification tasks, we use a general extractor. The general extractor is a kind of the general, for example, the image extractor or the language extractor, which is pre-trained on a very large data set. And we use a general extractor to extract the features for each of the instance in the task from the data set. And we average and we calculate the prototype, for example, the class center for each of the class. So in this way, the task representation is a set of vectors, one for each class from the task. And in this way, we only use one forward class for each task instead of multiple forwards. And how to learn the model representation as well as the task representations. The general extractor is frozen in our framework. We apply and we propose the model spider. We want to learn to rank pre-trained models with model and task representations. And we reformulate the pre-trained model selection as a learning to rank objective based on the historical interactions between pre-trained model and some tasks. If we find this model performs very well on a certain task than other pre-trained models, and we expect the similarity between the model representation and the task representation should be very high than other pre-trained models. So we formulate the pre-trained model selection as a learning to rank objective. And for the learning to rank, we utilize the learning to rank objective based on the softmax that mirrors the logic from a pair of model and pre-trained model when compared with other pairs. And we mirror the pre-trained the similarity based on a transformer. We input the model representation and the task representation, one for each class, into the transformer, and we use a similarity token, the learnable token, to calculate the similarity. This is a model spider. So in this way, we use a frozen general extractor, and we learn the model representation and the transformer to calculate similarities. And for an unseen task, we can calculate the similarity between this unseen task and the multiple pre-trained models, and assign to select the one or more pre-trained models. And for the supervision, we can utilize the sparse interactions between pre-trained models and the tasks. And we also consider use rank aggregation from several transferability scores. That is forward-based methods as a pseudo ground truth. That means if the historical information is very sparse, we can use the rank aggregation over the forward-based method to approximate a lot of supervision. And in addition, we also consider how could we take advantage of the meta representation, because previously we utilized the general extractor. The general extractor may not capture the detailed information from a target task. And now we use a re-ranking step. The re-ranking step means we first, for example, given the target task, the blue one, and we first use the general extractor to calculate the similarity between the target task and a lot of models, and we filter a subset of the candidates. For example, the top five pre-trained models based on the similarity calculated by the general extractor. For example, there are 2 candidates, and then we use the extractor from the selected candidates to replace the general extractor. That means we use the select pre-trained models to extract features to replace the task representations, and we then utilize the specific task-specific representations to calculate the similarity between pre-trained models and the tasks. And we find this based on this step, we can balance the efficiency and the ability of the model selector. And this is the result on image classification tasks. As we can see, the horizontal axis is the time, the smaller the better. And the vertical axis mirrors the correlation. The larger the better, the correlation between the selected order and the ground truth order between task and the multiple models. And the radius of the circle mirrors the memory, the memory cost. The smaller the better. And as we can see, that's the multiple previous transferability estimation methods. They could take a lot of time to get satisfiable performance. However, if we the K here means how many candidate pre-trained models we selected based on the whole process. When K equals 0, it means that we only use a general extractor to extract task representation and then select pre-trained models. So when K equals 0, it is very fast, and we can obtain satisfiable results. And we can increase K value here. For example, K equals 6, the 36. When when K increases, we use multiple. We use more than one. We use multiple pre-trained model candidates to calculate the task-specific embeddings. And we can see we can control the trade-off between the correlation and time by varying the number of K. So this is a model spider, and we use the learning-based methods to select pre-trained models, and we control the efficiency and accuracy trade-off. And however, as we can see, the ability of the pre-trained models also involve at first, the linear model or decision tree models could only be applied to predict new instances from a certain task. However, for deep learning models, we can see, especially for image or language models, we can apply the pre-trained models to new tasks with slight adaptation. However, and then we can see that for the language models or some foundation model, via language models, we can apply those pre-trained models directly to some new task or even new queries. So the evolution of the pre-trained models also makes the model reuse paradigm different. In other words, for classical models, when there is a heterogeneity between different tasks. For example, the different tasks may come from different domains or different feature spaces with different dimensional features. We need an explicit adaptation phase to bridge the pre-trained model and the target task. However, for some foundation models, for some nowadays foundation models, although there is heterogeneity between different tasks, for example, different questions from different domains, but we do not need to an explicit adaptation step. We can directly apply the pre-trained model, for example, the large language model. And the large language model has a zero-shot generation ability. That means it could be directly applied to a downstream task without explicit fine-tune or explicit adaptation. So this is the main difference from the foundation pre-trained models and the previous pre-trained models. The foundation pre-trained models, on the one hand, it have very strong abilities, and the zero-shot generation ability of the foundation models also decouples the selection and adaptation phases of pre-trained model reuse. Since we can directly apply the language model on different queries, we do not need to consider the adaptation step explicitly, or the adaptation step is not so important nowadays. And we need to focus more on the selection step. We need to select different language models for different queries. We also have some experiments to see that the effective reuse of foundation models still hinges on the selection. We need to, even there are different foundation, even the foundation models are very strong, and we can see their ability on different domains from a certain benchmark also varies. For example, for the large language models, there we can see the different foundation models, different language models, their ability are diverse across different domains or even different queries. So now, the input granularity the input of the foundation model may also shift from a full task to a single query. We want to select the most suitable pre-trained model for a given query or given question. We have tried to apply the model selection based on the previous meta representations on the visual language model, the model zoo, the large language model zoo, and the time series forecast model zoo. And in today's talk, I will focus on the reuse of the large language models. As we can see, the large language models are trained for different domains and exhibit distinct capabilities. Based on our evaluations, not only the specific fine-tuned language models, but also the foundation, the base language models. They have diverse performance on different tasks and different types of tasks or different domains. So we want to select if we can collect large language models, LLMs, to construct the model zoo. For example, there are 6 LLMs in this model zoo. And our target is to select the appropriate LLM for the current query. For example, this is a mathematical problem, a mathematical question. We want to find one model that has a very strong ability on the math tasks or on this particular task. Our basic idea is to construct a very strong model selector. So we utilize a large language model itself as a model selector. So we propose the capability instruction tuning because the language model is pre-trained based on some instruction tuning strategies. And now we want the language model to realize the types of question of the capability instruction. That means the capability instruction is composed by 3 parts. The first is the capability representation for a particular model. For example, we can pre-evaluate the model on different domains based on its records from the benchmarks. And we can describe the model's ability based on its performance on different types of tasks. And we also input the instructions of the questions. And we ask the model to predict whether the model can handle such kind of task. The training process is very similar to the model spider we mentioned before. That means we collect a lot of interactions between the models and on different queries, and we record them, and we use a capability instruction to fine-tune a certain language model, in a supervised manner. And we implement the selector in the form of an LM. As we see that we input both the capability representation, the first part, and the user instruction and the performance querying prompt are concatenated as an input for the LM. And finally, we use the score. We use the label based on the supervised, based on the historical records to train the LM. We have a very interesting experiment. Since as time progresses, new LMs are continuously released, and so the model zoo could be updated and expanded. At first, there could be only one LM in the model zoo. So for any questions, we can only use such LM, and the overall performance of the model selection or the model zoo is fixed. However, as time progresses, there could be one more LM. We want to assign different pre-trained models or different LMs for different queries. And overall, the performance could be increased. And we expect if there is a very bad LM, we need to avoid select it. And the overall performance could be will not change in this case. And finally, the performance should increase. We consider such kind of experiments based on a real-world model zoo with LM of 7 billion. The horizontal axis are the LMs based on their time of release time. The red line here means the performance of the model, of the performance based on the model selector. As we can see, if we can assign the pre-trained model, assign the right pre-trained model for a particular query, and then the overall performance will increase a lot. The overall performance can be better than the currently best performing model or the random selection, as well as some other methods. And we can see if we use if we can select some old model zoos, the older models in the model zoo, we can also surpass the new model, the advanced model with the same size, and we can even surpass the advanced model with larger size. So this experiment validates the capabilities of the pre-trained model selection, the LM reuse in this case. And the next step is in the previous work, we only consider how to improve the overall performance for example, the language understanding performance across different benchmarks. But in some real-world applications, we need to consider accuracy, but also the output quality, the latency, and the computational or memory cost when we select the LMs. So this is the pre-trained model selection over LMs has another name. That means the LM, that is LM routing. When we want to route the LM based by learner router, and the routing is the same as the pre-trained model selection, and the router here is a selector we mentioned before. When measures the LM routing performance, there also has multiple dimensions. We not only need to consider the accuracy, but also need to consider the total cost. And we can measure the performance based on the peak accuracy, the A2 here, the peak accuracy, based on a router by selecting the LMs, and also the area under the just like the AUC of this curve. Since if we have different budget to apply the area to route the LM, and we can have different routing strategies based on the accuracy, and we may also measure the query normalized cost. That is the C1 divided by C3. That is the minimum relative cost required to match the performance of the most accurate tested LLM, the strongest model here. And how could we complete the LLM routing? We can also use the previous mentioned method, but there are also some methods for the route to construct the router. The common way here is to use some feature extractor or some basic models to extract features for the user's instruction, as well as we can also learn the embedding, or we predict the performance directly. However, the objective here is we learn some regressors to predict the performance of the model on a particular query. For example, we can transform the routing problem into a regression problem that we can use MLP, the k-nearest neighbor, or the nearest class mean, the different methods to learn a predictor that could predict based on the features of the query and predict the performance of the LLM when given the query based on the historical interactions between the LLMs and the queries. So this is a common method in these years. However, we find a very interesting phenomenon. For example, as we can see, the core rate of the GPT-4 is the strongest model based on a routing benchmark, the open router. And we can see as the cost budget increases, when we have larger cost, we can use the more expensive models such as GPT-4. And GPT-4 is the strongest model in the benchmark. As we can see, this is the percentage of the core rate of the strongest model. Since when we route different LLMs, we want to consider both the small models and as well as larger models, since both of them have a kind of inductive bias and different capabilities on different queries. This is the performance of the oracle. And we can see when the cost is very low, when the budget is very low, the oracle always consider the small models because we do not have enough cost. And the cost could be seen as a kind of the money we pay for using the API of the model. When the budget increases, and then we can consider we can use the expensive model such as GPT-4. But in this case, we can see the oracle routers. It still consider there is still only a small portion of the oracle router to use the strongest model, the GPT-4. But how is the performance for the previous routers? We can see the results. We can see almost all the previous routers, they converge to utilize the strongest model when there are enough budgets. So they usually convert to the 100% of the core rate of GPT-4 when there are enough budgets. So we find as the cost budget increases, nearly all routing decisions degenerate into invoking the strongest model, effectively ignoring the rest of the model pool. We name this phenomenon as a routing collapse. It means that that's a failure mode in which small models are systematically ignored. They're becoming a key bottleneck in achieving an effective trade-off between performance and cost. Since we always want to assign the right model to different tasks instead of always using the strongest model. And we can see there is a large gap between the current LLM routers as well as the oracle. We do a kind of analysis. The first is we want to see is the generalization from the historical interactions to the unseen tasks is a bottleneck. And we find that even when we evaluate the previous routers on the training data set, we still observe the routing collapse. So the generalization is not a kind of the necessary condition. We also investigate is the decision sensitivity, the root cost. And we evaluate from two perspectives. The first is that we find that since the previous methods treat the routing task as a kind of regression task, and then and then we find since we cannot make the extreme accurate predictions for regression tasks, there is always a kind of the gap between the predict results and the ground truth results. And we find the errors between the prediction errors is larger than the performance gap between the top RM and the second best RM in the benchmarks. So this makes the feasible set margins are heavy concentrated near zero, and indicating that indicating a pervasive near tie among candidate models. And we also consider to inject noise into the oracle and observe that the performance may degrade with routing decisions gradually collapse over time. So if we inject noise into the learning signals, or even the oracle routers may degrade. So we find in this small margin region, since the performance gap between the top two RMs are not large enough, so the routing decisions become highly brittle. The tiny score perturbations based on the router can flip the top one ranking. And as budget expand, this instability systematically concentrates selections on the strongest models, leading to the routing collapse. And our solution is to reformulate the routing task as a ranking task. This is the same way we did in the previous model spider. So the first, we train the router based on the ranking task. Instead of predicting the absolute performance value of different RMs on the task, we predict the ranking, the comparison relationship between among different RMs given a query. So the ranking prioritizes the higher accuracy and the lower cost, and thereby we can incorporate the cost information and helping mitigate the near-tie case. And in addition, we also consider the joint feature construction. Since given one query, we consider to construct the embedding condition on the different RMs. So we use the RM as we use the different RM input to make the joint embedding between query and RMs condition change to be adapted based on multiple RMs. And we can see our proposed equal router can improve the utilization of the other models. And we can see the strongest model is invoked in fewer than 50%. And this is the dark red line is our equal router. And we can see that the core rate of GPT-4 reduces a lot, fewer than 50%, and indicating that the equal router allocates substantially more traffic to other models than existing routers. And we can also see that the equal router achieves substantially cost reduction when compared with other routers, based on the evaluation of the performance and the cost budget. And we can see our equal router achieves better performance given the budget. And finally, I also want to introduce one of our recent work. How could we extend the notion of the router to more advanced learning paradigm? So there could be a simple way we learn a router or select or pretrained model selector. That is, if we have a pretrained model selector that could be applied to different pretrained models. And we can learn the router or the performance predictors in this way. Given RM, given the given RM, and how could we represent this RM? We can provide a lot of queries from some public benchmarks. And we can also record the ability of the RM on this selected or randomly selected queries. So we can represent an RM based on its results on a subset of the queries. For example, we can provide 100 queries as well as the results of the RM on those queries and we provide the embedding of the queries as well as the right or wrong ability of the LLM. Given another, if we have and we want to predict, given another query, given an unseen query, how could we, what is the ability of the LLM on this new query? We can reformulate this task as a tabular machine learning task. For example, the instance is the embedding of the query, and the label is the right or wrong the LLM performs on a randomly selected subset with labels. And we want to predict the right or wrong the LLM will perform on a target query. We learn such kind of the LLM predictor, the performance predictor among multiple training data sets. There are multiple and a lot of LLMs. And we can see if we have such kind of the performance predictor, and then we can use it as a router. Since if we have a new query, we can predict whether the LLM could perform it well on this given query. The kind of the probability the LLM could rightly answer the question, and then we can select the given LLM among the model rule. And the right hand side shows the test results from the average of 12 data sets. Especially a lot of the mathematical data sets. This is one way we can construct a model selector. This is a router. And how could we extend the ability of the router? We can integrate the router or the performance predictor in the process of the LLM training. For example, if we want to train the LLM, usually we use PPO, a kind of the reinforcement learning algorithm, and in the policy gradient methods, they rely on a baseline to measure the relative advantage of an action, and they also require the value model to predict the value of a particular action. And for example, the policy model is rolled out in some cases. And we need to continually train the value model based on the rolled out results. So the computational burden here is very heavy, and we always use we want to utilize a kind of the strong value model and to accelerate the training process. And if we have a general performance extractor, we do not need to explicitly train the value model in the LLM training process. We can utilize the rollout results, and if there are multiple rollouts, we can predict whether this the current checkpoint of LLM can perform well on this particular rollout or particular action or particular query, and then we can weight different rollout selections and to update the LLM in a more efficient manner. So our approach treats the model's historical performance as the in-context input, and then we can use the pre-trained general performance predictor to elevate the challenge of requiring continuous and incremental updates of the value model. And we can see we can integrate our proposed methods into GRPO, and we can allocate different weights on 16 rollouts. We can since we can predict whether the checkpoint of the LLM here in this iteration could perform well on this in this rollout, and we can allocate more weights on the harder cases and less and the smaller weights on the easier cases. So we improve the training efficiency and the final performance of the LLM in the cases. So finally, let's conclude. So in today's talk, we see that if we can effectively taking advantage of pre-trained model resources can significantly enhance the sample and time efficiency of the machine learning paradigm. And the key lies in the efficient selection and adaptation of models. And among the foundation models, the selection become more important. And we show that by selecting the pre-trained models we can obtain better overall performance and smaller budget, smaller costs for a wide range of pre-trained models. And the ability of the pre-trained model selection can also facilitate the training process of LM. And we also have a survey paper on model reuse published in EGCAT last year. And the right-hand side QR code is the slide of our model reuse tutorial in IIII this year, the 2 weeks ago. Okay, and this is the end of this talk. Thank you very much.
Thank you very much, Han. Really, really good presentation, very interesting. And I think there would be plenty of questions, but we are running a little bit late and we need to go for the break. So I'm going to suggest that just on this occasion, we take the break and we go with some offline questions if you want. We've got the Telegram chat, and we may also speak to Han-Jia tomorrow, maybe during the winter school, hopefully in person. Okay? Thank you very much, and I'll see you all at 4:15 p.m. Okay?
Thank you very much.
Thank you very much. All right. Very good afternoon, everyone. Welcome to the last session of today's winter school. So next up is Professor Simone Calderara. He is a full professor at the Enzo Ferrari Engineering Department at Unimore in Italy, Modena, the Reggio Emilia, if I recall correctly, when I went to visit you back in May last year. And given his high performance research and impressive H-index, I would say the branding Ferrari clearly is a good fitting for him. He holds so many leadership titles, from Director of AI Academy to his roles in Ellis and CINA. I suspected he's actually using his own research in continual learning just to keep up with his own schedule. So it's probably very, very challenging. He's an expert in human behavior understanding in industrial and urban settings, and he'll likely know exactly how much you are enjoying his talk just by looking at the screen and looking at your posture and your face through the camera. When you're ready, the floor is yours, Simone.
Yeah. Okay. So good afternoon. So don't there's also a seat there if you want. Okay. So my talk will be about model merging. I think you heard the word this morning during one of the talk, and one of the lecturers mentioned the model merging. We will just go a little bit more into the details of model merging, starting from the easiest way to merge models to the more complicated one. And I'll also try to convey to you some motivation that stays behind the model merging and why it works. Okay. Let's start with something and let's see if it works. Okay. So this is how your GPT or LLM knows Kung Fu. Okay. And this is how model merging should work. So you should be able to plug something very, very specialistic, very, very expert in one field, and you should be able to acquire capability to an excellent level. So it means that our objective will be making Zoom work, and this is just one nice objective, okay, will be to find a way to plug something very specific into general purposes model, which is also one of the objectives we have for right now, because we are dealing with very huge pre-trained models that most of the time are some sort of monolithic application. We will see three different kinds of merging. So the first one is when all the models, so every ball here is model, all the models are trained on the same task, and we have different flavors, so different checkpoint, different initialization or something like this. And then we will switch to a more complicated setting in which every model has been trained on a different task. And what we want to do is to merge them to achieve something that is a multitask model through single task training. Okay. If you have questions, stop me. If you want to say something, stop me. And I also can convey it to the guys that are online. So let's start from the foundation. What is the meaning behind a merging of models? So basically, the easiest way to merge model is to merge their parameters. And the easiest way to merge parameters is basically to compute a weighted sum of them. So let's suppose I have model 1, 2, 3 up to m, and I want to compose them. All the models must share the same base architecture, so exactly the same number of layers and the same number of parameters. And then I can merge parameters just by taking a convex summation of the parameters themselves. Just to give you an intuition, is it the best thing to do? No. It is the easiest one? Yes. And usually, I don't know how much is your expertise in machine learning, but usually the first thing to try is the easiest one. And that's written on stone in machine learning. So if it works, you are okay with that, okay? So let's start with the single trajectory. In the case of the single trajectory, we said that in this case, let's suppose every ball is a checkpoint. So it's a point during the trajectory of the training. So I don't know, I'm training for 20 epochs. Every ball may be one epoch, checkpoint. Or I don't know, after a certain number of iteration, I'm picking a checkpoint and I'm freezing stuff for a little bit. And this is one of those balls. So my objective here is to verify that probably the best thing to do is not to pick the last checkpoint, but it may be to mix the information from different checkpoints of the same model over time. And that's basically what happens here in the polyacropert averaging technique. So this is the usual SGD update. You have model at time t, you compute the gradient, and then you update the weights. While instead, in the polyacropert averaging, what you are doing is computing a running average of the parameters. So you're not just updating them, you're picking the parameters before, you're downsizing their value by a scalar value, and then you're adding the new parameters, okay? If you, instead of t, with the throne, wow. Okay. So if this t is not just an iteration, but is a checkpoint, what you're doing is simply averaging the checkpoints over time, okay? What are the consequences of this procedure? So basically, it's reduce the variance of the solution. So it means that the variance of your parameters during the training procedure tends to be a little bit more contained. And this is helpful because it stabilizes the training trajectory. So if the variance is reduced, it's definitely better. And it's also the foundation of a lot of modern variation of the gradient descent that take into account the checkpoints over time. And if you go back into the literature of the past, let's say 10 years from now, without giving exactly a name to this procedure, it's present in a lot of practical way to train your network. So you can read, for example, we take the average of the parameters over time, we average the last 5 checkpoints, and so on. So basically, this is nothing new. So people usually tends to do it, but without studying effectively why it worked. It empirically worked. So a lot of people did it in the past. But right now we know exactly that this basically stabilizes the training trajectory. So there are plenty of different ways to merging parameters in the case of single trajectory. So another one is the so-called tail averaging, in which you are picking parameters inside the window. So let's say the last 4 checkpoints, and then you're taking the average over there, not over the full trajectory. Or a well-known technique that is also plenty used when you perform unsupervised feature learning, that is the exponential moving average. You should be familiar. Usually when you have 2 models, there's the slow model and the fast model. The slow model typically it's trained with the EMA technique, okay? What you're doing basically is picking the current checkpoint, you are downgrading it, and then just multiplying by alpha, and then adding the last checkpoint multiplied by 1 minus alpha. Okay, so typically alpha tends to be high. So what you're doing is updating your checkpoint in a very slow way. So it should be very stable. Okay, questions? Can you follow me? Yes, wow. Another technique, which is critically a variant of what I've said so far, is the LAW technique, in which what you're doing here is to randomly sample K checkpoint from the past. It's not necessarily the last K, and then put them into a FIFO queue, FI, FO, first in, first out. So the oldest one is also the first that you pop out, okay? And every fixed number of checkpoint, you do the sampling again, and then you recompute the average of the gradient over those checkpoints. It's like adding some stochasticity to the average, okay? It doesn't mean that those checkpoints should be the last k. You can sample k of them out of a number that is big of, greater than k. And again, it helps to reducing the variance because the random samplings helps to, well, not follow the last current mean, but taking the sample mean, and then it reduces the variance naturally. So if you don't trust me, just look at the plots. This is the current training of ResNet using gradient descent, the stochastic gradient descent with Adam, with whatever you want. And this is the LAW version. So this is in terms of the loss, this is in terms of the accuracy. So if you take a look, the loss function is definitely more stable due to the averaging. And you see you don't have all those peaks. And then it also converges definitely faster. But also the same, it's true in terms of accuracy. And there's this huge gap. So after 20 epochs, you can converge definitely faster. You can reach the same performance of the original model after 6. So it can be used as a procedure to speed up the convergence of your gradient descent approach. So basically, if you recall how you usually train your neural network, you are already doing something like this somehow. And I would be super happy if some of you can tell me where. When did you apply averaging in your conventional neural network training? Yeah, but when you did the computation of the gradient on the batch, okay? When you do batch gradient descent, you're averaging the gradient, and this helps in reducing the variance of the gradient. So if you project this concept to checkpoints, you are reducing the variance of the full trajectory in the loss landscape space, not just a single iteration of your gradient descent. But basically, it's the same concept, okay? So let's go with the last method. This one is one of the most effective. So if you want to try something, this is really easy to implement, and it's also quite good. And the author said that, let's suppose you start pre-training your method with Adam, with gradient descent, with whatever you want. And after a portion of pre-training, let's say 75% of pre-training, you start using this update rule. What does it mean? It means that you fix n, which is a number of steps, and after n step, you pick the n+1 parameters set, this theta here, and you sum it up to the current parameters multiplied by n and divide by n+1. So it means that you are taking the average, but after n random steps, subsequent steps, okay? Not every time. This set, which is the newest one, weights 1 divided by n+1. So it weights really low. It resembles the exponential moving average procedure and so on. Okay, so it's a way to slowly update the parameters, but at the same time, you are exploring the space. Another thing is that in this case, they are using a learning rate that allows you to explore the space. So it means that those parameters may change a lot with respect to the past, but since you have this update equation, you are keeping them consistent, and you are keeping them smooth sometimes in terms of trajectory. Do you see that? Okay. And again, if you don't trust me, just take a look at this plot, which is quite interesting. Let's suppose we have 3 different set of parameters in which the model was at convergence. And this is not the training loss landscape, but it's the test loss landscape. So this is done on the test set. And what to observe is that W1, it's a perfect solution during training, but it's not the perfect solution of the test set. This is basically due to the fact that we always somehow have some sort of generalization gap between the training and the test. And this is due to the IID assumption you should be all familiar with that cannot be fulfilled perfectly in real life. So basically you have a shift between the loss landscape of the train and the loss landscape of the test. And if we take this plot and we observe where is the optimal point, you can see that it's in between different checkpoints. So it's in the middle. So it suggests us that if we combine the checkpoints and find the average over there, we should be better than the original model on the test. Okay, and this is also true here. This is the train loss, so this is the optimal solution. But again, this is the test loss of the same data set, and the optimal solution is over there. So it's far from training. So if you take the average between different epochs, you will reasonably fall there, and it allows you to generalize better. If you don't trust me, or you have something against what I'm saying, just tell me. Okay, but why basically averaging works? The fact that network parameters can be linearly combined is due to this property. You should be familiar with that is called the linear mode connectivity. So it means that under certain conditions, and we will get back to them later, you can linearly interpolate between modes of neural network, so between different solutions to different problems. So basically, in this case, the problem is the same. The data set is the same, hyperparameters are different, so you have different loss basing. And moving along this line, you are moving along a path in which the loss stay low. So it means that if I'm moving between this solution and this one linearly, the loss will not increase. This property tells me that somehow, if this holds, I can combine solution by linear combination without altering the loss function. So, keeping my solution to the true problem, so my original loss function, as low as possible, so as low as in one of the checkpoints. Okay? Did you get it? Yes? So practically, what does it mean? It means that I should verify that the linear combination between two different checkpoints, let's say set of parameter 1 and set of parameter 2, and the loss computed on the combination, the model obtained by linearly combining the weights, is equal to the average of the two losses. This is called the loss barrier property. If this holds, it means that the models are linear mode connected. So basically, it means that if I'm moving along this path, I'm not worsening model 1 and model 2. I'm just following a minima in the loss landscape of the two models. Okay? And with alpha, you can control how far you are going from model 1 towards model 2. So if we use, I don't know, alpha 1, it means that we are here. Alpha 0, it means that we are here. Alpha from 0 to 1, it means we are moving linearly along this path. Sometimes, if you compute this empirically, it doesn't work. So it's not always true. It's true under certain condition. We will revise some of them later. Just to give you an idea, we usually do this kind of plot. So on the left, you have model 1. On the right, you have model 2. And this is the interpolation coefficient, so the alpha. And by changing the alpha parameters, when alpha is 0, we are picking the error of model 1 and model 2 alone. Here is the same. When you combine them, you can see that we are breaking something here, because the error is increasing. So it doesn't mean exactly that the error stays low. So this is the ideal case in which the model is perfectly linear mode connected between two different checkpoints. And this is the case in which the model is not linearly mode connected between two different checkpoints. So our objective is, if we fall in one of those situations, to try to achieve a better linear mode connectivity in order to merge the parameters through a linear combination. Okay? It's not always easy, but sometimes it is. One of the things we can do is very intuitive. I try to let you grasp the intuition before. So let's suppose we have model A and model B, same architecture, two different checkpoints, checkpoints A and checkpoints B. Okay, as Simone seems to be a mystery. Happy to. Okay. So let's suppose we have two checkpoints, two different models. Let's start with different type of parameters, same dots. Okay. When we reach convergence and we look at weight 1 in model A, first layer of model A, weight 1, first layer of model B, weight 1, it's not always the case that those two weights means the same stuff. They can be different weights. We start from different type of parameters. So probably parameter 1 can participate in some functional with a certain condition, and in model B, it can participate to a different functional with different condition. For example, if you pick a CNN and you look at the kernels, if you start from different parameters, the kernel order is not guaranteed. So the first kernel for one network may be the third kernel for the other one. Okay, this may happen. It's totally normal. But if those two parameters mean something different from a semantic standpoint and from a functional standpoint, you cannot merge them. You're merging an apple with a motorbike. So you cannot take the average of those two. So that's why one of the ways to increase the linear mode connectivity property and reduce the loss barrier is to find permutations in parameter space to let them somehow match a little bit more. So what I can do, just think about the linear layer. I can always pick the original set of parameters, apply a specific permutation to them, and then compute the output of the layer. So multiply it by x, by the input, and then applying the anti-permutation after that in order to reorder the output and make it functional equivalent to the original function. So the computation stays the same in terms of input and output. What happens is that in this procedure, I'm not using W1, I'm using W1 first, which is a rearranged version of the parameters. And if I rearrange them in order to be compatible with model B, I can sum them up. And this is what it's usually called linear mode connectivity modulo permutation. Okay. This is also one of the basics of this specific algorithm, which is called git rebasing, in which the basic idea is to create some sort of functional equivalent between two different models, just by reordering the parameters and make them matchable in terms of semantics meaning. And this is usually done through either a weight matching. So I'm picking the weights, I'm computing some sort of, I don't know, the differences of whatever, some sort of matrix, and I try to find the best permutation in which my cost function is at the minimum, but it is a quadratic problem. You have weights here, weights there, so a very huge cost matrix here. You can do the same with activation, for example. Yes. Yes, Carlos. So it works also on CNN, since a CNN you can linearize it and transform in a local linear layer. So basically it's the same from a functional standpoint. It works also on transformer, because transformer, except for the attention, all the others are linear projections, so it are linear layers. And for the attention, there are solutions. It's not exactly git rebasing. There's one paper in the world probably that works with transformer and rebasing, and it's from us, that is called transfusion. Okay. I'm expecting another question. What if the architectures are different? Can you write it down? No, it's okay. Okay, no. We will go back later. So we can do it on weights. It depends. If you have a very small network of you are doing one layer at a time, you can do it with weights. But if you are taking into account the whole network, it's a problem. And or you can do it on activation. In the case of activation, what you're doing is basically assign the activation according to a cost function, and in this case is a bipartite graph assignment problem, so you can solve it with the Hungarian algorithm. Otherwise, you can use a fully learning-based approach. So you can just write down as the loss function, the loss barrier I've shown you before. So the loss of the interpolation minus the average of the loss, LW1 plus LW2 divided by 2, and we want to minimize this quantity. And we have some variables, and those variables are the permutation, and you can use as GD for learning the permutation. But keeping in mind the fact that in this case, those permutations are not exact permutation, because a permutation matrix should, for example, have at first numbers inside the matrix that are either 0 or 1, and they must sum up to a fixed number. So you need somehow to fix it in order to be a permutation matrix. This is just a, let's say, continuous version of the permutation matrix. So it doesn't give you exactly the functional equivalence. While those two, yes. So again, if you don't trust me, this is the same plot as before, but after applying permutation. So you have model A and model B. This is without doing anything. And you can see that if I interpolate between them, there's a clear increase in the loss barrier here. So it means that those two models cannot be interpolated. And this is the result applying different permutation. So you can obviously see that the loss barrier reduces, so I can safely interpolate between A and B without increasing the loss so much. So I'm achieving linear mode connectivity again. Okay. So now the question is, do we always need something like rebasing? So do we always need to find a permutation in the weight space? Finding a permutation in the weight space is super costly from a computational point of view. I need to align a lot of parameters. My friend is from combinatorial optimization, and when you have 1 million weights here and 1 million weights there, it's 1 billion cost matrix, and solving a combinatorial optimization problem here, it's really a mess. And so, obviously, if we can avoid it, we should avoid it. And there are some conditions in which linear mode connectivity is quite granted by making some assumption about the models. So let's revise it together. So the easiest one is this one. Let's see if somebody of you can guess what is the meaning of this weird drawing. I'm open to hypotheses. In the meanwhile, I just trick myself because it's super hot in there. Yes, exactly. Very good. So can you still hear me? Isaac, wave your hands if you hear me. Okay, super. So it means that the model is trained on a checkpoint. So it means that all my fine-tuning, all my checkpoints that I want to merge start from the same pre-training. Okay? So we start with a very huge pre-training, I don't know, typically done on ImageNet or the clip visual encoder, whatever, and then, or an LLM, for example, and then we compute fine-tuning starting from the common pre-training. If we are doing so, and if the pre-training is huge enough, this somehow allows those checkpoints to be a little bit linear mode connected. And again, this is a plot that shows something like this. So I'm picking two different fine-tuning starting from the same pre-training, and this is their loss barrier. So it means that those two models are perfectly linear mode connected. And then instead here, I'm picking one fine-tuning, just take a look at the blue one. I'm picking one real fine-tuning, and the second one is a model that was randomly initialized with random weights. So it's a model that exactly shouldn't be linear mode connected with the original one. And if you see, the loss barrier goes up, okay? And then you also have to mix an experiment in which the model is totally random, and again, the loss barrier goes up. But what is interesting here is that most of the time, if you start with a really, really huge pre-trained model, you can achieve linear mode connectivity just by fine-tuning and keeping different fine-tuning, and you can interpolate between them linearly. And it works. Yes.
Are you, in all those cases, are you assuming that you are solving the same task with the same data?
Yeah, at the moment, yes. At the moment, yes. Later on, we will go into different tasks, different data. Okay, later on is now. So now we have different training trajectories, same data, okay? So what does it mean? It means different models trained on the same data set. It shouldn't be exactly the same data. It can be a different sampling from the same data set, but basically it's the same data set. So this goes for a well-known technique in machine learning that is called ensemble learning. You should all be familiar with what ensemble learning is. And in particular, basically, we are in the case in which we are applying some sort of bagging techniques. So we are computing different bags, we have different models, and we can take the prediction by using, I don't know, the mean or a majority voting criteria. And it guarantees that if the errors are correlated, the final performance will be better or at least equal with the best model of the ensemble. And this is theoretically guaranteed. Okay? What is the problem? The problem is that, let's suppose this is an LLM, let's suppose this is an LLM, and this one 2, and this one 2, and again. We have 6 LLM, and in order to compute the ensemble, we should do 6 forward, which is super expensive. We don't want to do that. Okay, the final performance is good, but I'm increasing by 6, 10, 20, 100 the number of computation for computing these performances. So what I want to do is, can I do the same with just one forward? And the answer is, I should merge all this model into one. Okay? This is exactly what I said now. And again, if you don't trust me, let's start from this pre-training. So the star is a pre-training. Again, those are the classical loss landscape plot. So this is the loss landscape. And this is the training. And if you observe, you can see that different checkpoints, so different training of the same data set, different models, fall into a low loss area in the loss landscape in the case of training loss. But again, if we move to the test, and this is the test loss, the best solution lies in between them. So what does it mean? It means that I can train effectively, but when I train, it is true that I'm solving a problem, but I am also somehow losing something in terms of generalization. And again, this is also the case here, and that's pretty the same test. So you have one solution here, which is a good solution for the training, another here, which is a good solution of the training. But if we switch to test, the best solution should be here. So in between the solution we achieved so far. So the first way to deal with this is the so-called model soup, which is basically the extension of what we said before for the single trajectory case, to multiple models. So let's suppose we have M models. I'm picking the parameters, I'm computing the average, and I'm obtaining the so-called soup. What is the difference with respect to the ensembling? It's that here I'm performing just a single forward pass, while instead there I should perform big M forward passes. So it's definitely more efficient. And it shouldn't be enough if the ensemble performances and the soup performances are not correlated. But we can empirically show that in this case, the soup performances and the ensemble one are strongly correlated. You can see those plots. So it means that even taking the soup, I can achieve quite the same numbers of the ensemble, but just by taking one single forward pass. So it's super useful. And again, what we are doing, it's not very complex math. We're just doing summation and averaging, but we should pay attention to the concept behind that. So what happens if we are complicating things again a little bit? And now we have also different data. Different data can also mean different tasks. Okay, so let's suppose this is a classification problem on natural images. This one is on satellite images. This one is on, I don't know, industrial parts and so on. Or in the case of LLM, this is an expert in mathematics. This is an expert in stemming out the names. This is an expert in sentiment analysis and so on. Okay, so we have different data sets that can mean different tasks. It can also mean the same task. It depends on your problem. Okay. Here, the problem is that I'm no more sure that the parameters means the same thing. Again, I'm in the original case in which if I'm picking model A and model B, parameter 1 of the first layer of model B and parameter 1 of the first layer of model A probably means something different from a semantic standpoint. And if it's so, it's a problem because it means that I cannot merge them directly. But if we take a little step back, before we observe that when we fine-tune different models on the same datasets, so we start from the same pre-training, they converge to a region in which I can interpolate them. So we said before that somehow the loss barrier is quite small. So let's check if it happens also for different datasets, different tasks. And surprisingly, it happens that we can move along this path here, and those are not so far each other. So it means that somehow, even if the datasets are different, but the task is the same, so the number of classes and the task remain the same, those models may be close in space. If you don't trust me again, let's try to summarize with this sentence. So it means that when we start from the same pre-training, we pull the task region close each other. And since they are close each other, it's very easy to move from one region to the other one. Different thing is that we can move linearly. Okay, but we can move. So that's why I would expect that just by taking the model soup, but with different model strains on different datasets, should work as good as the original model soup. But this is not the case. If you take a look at here, this is the multitask model. So basically the model trained on all the datasets, all the tasks. And this is the merging of and model train each one on a single task. And here it's a quantitative evaluation of that. And you can see there's a huge gap over there. This suggests that probably just by simply averaging is not enough in this case, because it's true that the region, the task region are close in parameter space, but it's also true that there's not a linear path connecting them. So we need to find another way for merging the parameters that it's not the plane mean, okay? And that's why I'm showing you some advanced method that works in practice. So basically, when you perform the mean, you are making this assumption. That is the so-called isotropic assumption. So basically that every checkpoint, so every set of weights the same in the average, okay? So it means that all the weights, all the checkpoints, all the models are as equally important as all the models of the soup. This is not exactly a good way to do it, because if you remember, every neural network has some parameters that are more important than another. And if you pick, for example, an LLM, there are a lot of parameters that are totally unuseful for the computation. There are a lot of studies that says that those models are highly redundant. But this is also true for very huge VIT and so on. You have plenty of parameters that are not the key parameters for a specific task. And it is also the case that if you are solving different tasks, different parameters may assume the role of key parameter for that specific task. Let's still start from the same pre-training, so same architecture, same huge pre-training, different fine-tuning on different dataset and even different tasks, okay? So what I'm suggesting to use, but I'm not suggesting, those guys are suggesting to use it, is to use the Fisher matrix. What is the Fisher matrix? It's basically a matrix computed by computing the gradient. So you have a number of components equal to the number of parameters times itself. So basically, it's a matrix containing the square of the gradient. It is said that the Fisher matrix is somehow an approximation of the Hessian, which is the second-order derivative of the gradient there, okay? And if you recall, I don't know, Calculus 1 or whatever from the high school or from the university, the Hessian is strongly related to the curvature. The more is the curvature, the more I'm confident this point in which I'm computing the curvature is a very certain point. The less is the curvature, I'm on a flex area, so it means that this point is related to some uncertainty. So think about a point in which the gradient is 0. If my curvature is 0, so if my Hessian, if my second-order derivative is 0, I'm in a flex. So even if the point make the gradient fall to 0, this is not a minimum. So it's a point in which I'm really uncertain about its effectiveness. While instead, if I'm in a true minima, which is a point in which my gradient is 0, but my Hessian has a very high value, it means that there's a huge curvature there. So it means that it's a real minima, a very strong one. So what I'm suggesting here is weight every parameter, every checkpoint, by the value of its Hessian, and merge certain parameters with a huge coefficient and uncertain parameters with a low coefficient. So what will happen? Let's take model A and let's fix its certain parameters and use them with the high coefficient in the merge. And then model B, if it's using different parameters from the one from model A, let's assign to them a huge coefficient in the certain one and a low in the certain one. And by doing so, I'm reducing the interference between parameters. I'm overwriting the one that are not so certain in one model while keeping the one that are very important. And this is the so-called Fisher averaging method, okay? There's one problem here, okay? Risk silence that has been zoomed. It's from 7 minutes ago, so let's suppose it didn't happen. Sorry, I missed the question, but it was from 7 minutes ago, so probably you're not speaking about this part. Okay, so the problem here is that computing Fisher matrix is again super costly. If it's a matrix number of parameters times number of parameters, so let's pick a small model with 1 million parameters. It's 1 million times 1 million matrix. And it also involves computing the gradient and taking the square value and taking the expectation of over a lot of data, because what we are computing is the empirical version of the Fisher, not the theoretical one. So this is usually not feasible. So what you usually do is approximate the Fisher again. And one of the approximation is the diagonal version, which is the most approximated, the strongest approximation you can take. You just compute the square of the gradient and you put it along the diagonal. Okay. This is also the approximation that was used in WC and so on methods, if you are familiar with continual learning architecture.
I've also seen that sometimes you use a block diagram.
This is another type of approximation, which is very nice, that is called the K-FAC approximation, the Kronecker factored approximation. So you approximate the full Fisher by some block in which you are computing the Kronecker product, and you can do it layer-wise. So it really reduced the number of computation because the number of parameters at the layer are different from the number of parameters at the whole network. And you can compute some sort of full Hessian approximation by using the K-FAC. Otherwise, it's quite impossible. So you need absolutely to neglect most of the contribution between weights, and you're just keeping the diagonal. And we have applied, in the case of merging, several regularizators based on the K-FAC approximation. And it works quite well, even in the case of model merging. So if you're curious about that, he's your guy. Okay. What other option we have? So if we don't want to compute the Fisher and we want to work layer-wise, we can take a look at this method that is called regmean. So basically here, the idea is to set up an objective which tells us something like this. I want that the merge, so the merge model stays in terms of output as close as possible at the individual models. So I want that the merge is quite as good as every individual model that was trained on every different task. Okay? Just by doing so, if I can optimize this quantity, I can obtain WT, which is the objective of this optimization, by which its output is very close to every individual model, which are my experts, okay, my Kung Fu experts here. Just by taking a look at this problem, it's very easy. It has a closed form solution, which basically involves computing this power in explicit, and then just by rearranging the matrix and taking the inverse, you can compute the solution for WT. And that solution tells us something like this. So basically what I have is the checkpoints, so the parameters of every single model. And instead of weighting them for the Fisher matrix, I'm weighting them for the covariance of the feature map of the input. So what I'm picking, it's a batch of data. I'm computing the covariance of the input to a single layer. I'm using it as a weight for merging the models. And then this is just the inverse to make this number not goes up to 1. And this gives me the merge for one layer. And then I'm moving to the next one, and I'm doing the same. And then I'm moving to the next one, and I'm doing the same. Keep in mind that when doing so, this xi here, which is the input to a specific layer, when it moves to the second layer, I'm not using the merge version. I'm using the original version. Okay? So I can pre-compute them on my pre-trained model, and those stays the same. So I can pre-compute them for a set of data, and then I can use them for a linear-wise merging. Just by doing so, for every layer, I got the merge set of parameters. Okay, questions? In general terms, this is not more effective than Fisher, but in practical terms, it is, because computing the Fisher, it's very complicated. And then you need to resort to some sort of approximation. So if you use K-FAC, this is definitely worse. But if you use diagonal Fisher, which is the case here, just by using regmean, it produces better results. Okay? Questions? No? Okay. Is this method under some hypothesis like share parameter semantic? Yes. Haha. It was the answer, or it was the answer to my question? Okay. Not exactly. The hypothesis we did to make the parameter means the same is that we start from the same pre-train. Just by doing so, well, the structure of the parameter is given by the pre-training. So what you can do with fine-tuning is change the parameter a little bit, but you cannot change the structure of the model. So if you, I don't know, pick the clip visual encoder and pre-train it on ImageNet or on a huge data set, and then you fine-tune it, the meaning, so the structure of the parameter stays the same. It doesn't change so much. It changes if you start with different type of parameters, different data set, and so on. So in this case, the structure may change. But if you start from the same pre-training and fine-tune stuff, you shouldn't revert to permutation or some complicated stuff to make the parameters match in terms of semantics. Okay? We are not exactly, I'm using wrongly the word semantics. It's more related to structure. So it means that one parameter means something in terms of functional computation. Okay. Okay, so putting things up together, we have seen three methods for merging different models. So the basic one, which is the isotropic Gaussian, doesn't work. We have the Fisher averaging, in which we weight through the Fisher matrix the parameters. It basically gives more important to the more certain one and less important to the more uncertain one through the Fisher matrix. And then if we don't want to compute the Fisher, we can compute the covariance of the activation with the rank-mean approach. And in this case, we can do layer-wise. So you can also apply it to very deep network. And then you can do one layer at a time. Okay. Questions? Let's again take a little step back and try to approach the merging from a slightly different point of view by introducing a new concept here. After the fine-tuning, I can always compute the difference with respect to the pre-training, and I've got a delta theta, which is an update that I should apply to the pre-training to achieve my fine-tuning method, okay? This delta theta takes the name of task vector. So it typically means that starting from my pre-trained model, if I'm fine-tuning it on satellite images, and I have a set of delta that I can apply to the pre-trained models, this is the delta for my task training on satellite images. And if I have a delta that I can apply to car images, this is the task vector that I can apply for making my pre-training network learn to classify cars and so on. Okay, is it clear, this kind of concept? So what I want to do is, if my task vector can be linearly combined, I can do the same stuff I've done before by merging models, but in a more structured way. So since a task vector identifies in my parameter space a clear direction, it's a vector, which has a number of components equal to the number of parameters, but it's basically a vector. So what I can do is applying vector algebra to it. So I can combine two vectors by computing the resulting one. I can negate one vector, meaning that I'm moving the model in the opposite direction with respect to my fine-tuning. So it means that I'm trying to remove the component that I learn with this fine-tuning from my model. That is also called forgetting, or it's called, I'm missing the word? Unlearning, exactly. Or you can perform some analogies. So if my vector works like this, and it is in relation with another vector with a fixed relation, I want to learn a vector C which stands in the same relation between those two. Okay, so I can somehow apply basic algebra operator on those vectors if and only if those vectors can be linearly combined. Okay. So how is it different from the parameter averaging we have seen before? If we start from the same pre-training, basically under the condition that the lambda sum up to 1, those two formulations are, from an algebraic standpoint, equivalent. It is exactly the same. So here, if you substitute this theta with the pre-training plus the increment of the fine-tuning, and then you can take out the pre-training from the squares here, because it's the same, so you can take it out, and just by rearranging things a little bit and keeping in mind that the sum of lambda I is equal to 1, basically you come up with this equation, which is exactly the same we have applied here. So we can, instead of merging the full checkpoint, we can merge just the task vectors. It's the same if we start from the same pre-train. So let's suppose we have a pre-trained model. We keep those weights here. Instead of computing the full weights, we just compute the delta and we store them. And we can perform all the merge operation only on the delta. We don't need to merge the same set of parameters, because every new checkpoint, every new model can be expressed with a different with respect to the original pre-training parameters, okay? So we said before that we want those task vectors to be linear and to be combined in a linear way. And the best thing to do is remember that usually if we think about our network and if we think about the manifold spanned by the weights, this is all but linear. Okay, it's typically a manifold, it's typically highly nonlinear, it's typically characterized by some geodesic distances in the parameter space, and so on and so on and so on. But what we can do is to take some sort of Riemannian approximation, so we can fix some important point on the manifold and try to put a plane on top of it and reproject the parameters onto the plane, and then we obtain a linearized version of the task vector. And since this is a plane, or an hyperplane, obviously, here it is by construction that I can linearly combine those vectors because they are defined on the plane. Okay, so I'm using planar algebra here. So the question is, okay, very nice, but when should I linearize the model? So is it okay to perform my fine-tuning and then linearize my model and then combine the task vector here? Or is it better to linearize with the model before the fine-tuning? So linearize the pre-training and then fine-tune. Well, empirically, we can see that if we perform our nonlinear fine-tuning and then we linearize the model, the final performances of the model really drops a lot. And this is basically something that we can observe empirically. It means that the way we linearize it does not exactly represent correctly the learning trajectory that we use during the fine-tuning. If you don't know how to linearize the model, you can check this paper. There's the code here. Otherwise, it's basically to compute the NTK version, the neural tangent kernel version of a model. So you need to compute the Jacobian and so on, and basically apply the Jacobian to the original set of the logits of the model, and it gives you the update you should apply to the logits. Well, it's really a bit of tricky from a mathematical standpoint, the NTK framework, but I think it's a really nice theoretical framework to explain the behavior of neural networks. So if you have time, just take a look. It's very, very nice. And it tells you that you can study the behavior of a neural network as from a linear standpoint, just by linearizing the model. So transforming it from a very complex nonlinear function to a simple linear projection, okay, in the NTK. And since it's a kernel, if you are familiar with kernel theories, you can apply on this kernel all the kernel theories and properties you know. So you can compute the spectrum of the kernel, you can compute the degree, you can perform some kernel tweaking, and so on. So basically, it allows you to apply all the experience you have with kernel learning on top of it. But getting back to the problem here, the suggestion is to linearize the model before the fine-tuning. So fine-tune in the NTK regime. If you do so, you can observe that this empirically even outperformed the nonlinear fine-tuning. And and this is basically due to the fact that, if you fine-tune in the linearized regime, we can observe, and this is also what the paper states, that if we compute the eigenfunction of every kernel, those eigenfunction has a spectrum that is non-zero only on the data related to a specific task. So it means that my kernel, if I'm changing the dataset, so I'm using the dataset of task 2, the kernel defined by model 1 on data from task 2 drops to 0. So it's not a kernel anymore. Okay? And this is also the case for model 2 on different data, except from the data of model 2. This allows to disentangle the weights. So it means that I can somehow fine-tune by making the weights disentangle each other. And if they are disentangled, I can easily combine them without hurting the performance. So basically, I'm combining some sort of orthogonal direction. We don't have a theoretical reason for this. It's just empirical observed. This is exactly the visual representation of that. So let's suppose this is the D1 dataset and this is the model 1. This is some sort of spectrum or, the response of the network on the data of model 1. And by applying task vector 1 here, I have some responses. But when I move to data from task 2, my network stays flat. So it doesn't add anything to that. So it means that the weights are disentangled. And here is the same. So when I combine them, you can see that this response here and this here does not overlap. So I'm not creating any interference. Okay. This can be obtained by linearizing the model and fine-tuning in the linearized space, or can be obtained by using different techniques. One of them is this one, which is called the gradient mismatch function. And basically here, the idea is doing the same that we did before with regmean about the output, but this time with the gradient. So what I want is that the gradient computed on the merge of the multitask merge of the models stays as close as possible to the gradient of the individual models. So it means that I don't want to, for every set of data, and here I'm picking a batch from every task, I want that my multitask model behaves as similar as possible in terms of learning functions, so in terms of direction in the parameter space as the original ones. And again, since the formulation is almost the same, so there's not a square here, but we can put a square here without creating problems. Without a very big surprise, the solution will be the same of regmean again. So if you take a look at this, we still have the Fisher here. This time I'm decomposing the Fisher into two terms. I have the Fisher of the pre-training and I have the Fisher of the fine-tuning, because I decompose the weights into the weights of the pre-training and the weights of the and the tau that I'm applied to the weights of the pre-training. So depending on the set of weights I'm computing the derivative, I can decompose the Fisher in each one of those terms. And what I'm weighting is the task vector, again, according to the Fisher. Again, this is something that rescales the results, but you shouldn't. You can get rid of it from a conceptual standpoint. So I'm doing basically the same I've done with regmean. So what I'm doing is to weight the task vector according to the certainty of the direction. In this case, it's not of the parameters, because tau represent direction and not parameters. Yeah.
How does this relate with LoRa? Because you can train several LoRas and combine them. I did it, but without any notion of the analysis. Is similar to this.
Right. In the case of LoRa, it works because LoRa is low rank. So since you are low rank, there are very few conflicting directions. So it tends to work, not always, okay, but it tends to work for this reason. So the more your space is low rank, the more direction you have here, the more interference you have when you merge them. That's basically the explanation I can give it to you. But there are also some merging techniques that works with LoRa and are definitely stronger than the linear combination. It is the same if you are applying the first equation we have seen today, the parameter averaging, which is what you are doing basically when composing LoRa right now, or a more complex technique. There's 10, 15, 20% points of gap. Okay, let's skip it because it's not funny. Okay, let's see another method. And again, recall that we have task vectors, and task vectors represent direction into the parameter space, is the update which should apply from starting from the pre-training. And this method, which is very famous, I think it was mentioning also this morning, somehow, very quickly. It's called TIAS. Start from this idea. Since the task vector represent direction, and basically are represented as a set of direction, one for every weight. So on every axis, I'm applying an update, okay? One for every weight. I can observe two things. First, if the module of the update is small, I cannot trust the direction so much. So it means that if the module is very close to zero, the direction tends to be a little bit more random. I can trust the direction if the update is significant. And the second thing is, when I need to merge two sets of direction, if on one axis, one direction points toward up and the other points toward down, when I'm merging them, I'm creating a problem in which one tends to move the parameters up and the other tends to move the parameters down, and they cancel each other. This results in a merged parameters, which is not good either for task one or task two. So what TIAS is doing is addressing those two problems. So the first one is get rid of the direction, which has a very low module. So don't consider them in the merging. Don't use them. The second thing is select the sign, so plus or minus, compare it with the second task vector, and keep only the updates which shares the same sign and merge them. Okay? Oh. The sign is it a plus or minus? Okay. No, you have two task vectors. So if they are the same, you keep it. So plus, plus, minus, minus. If they are different, you don't perform the merge here. You keep the pretrained. So that's basically the algorithm. This is what exactly I've told you before. So at the beginning, you trim. So you reset a set of updates, which has a module less than a certain threshold. It's a percentage typically. So let's suppose I reset the 10% of the weights. So I'm keeping the one by which the module is the least 10%, and I squash them to zero. And then elect sign. So keep all the direction that has the same sign and merge only the update with the same sign, and the rest you use them equal to zero. So you don't use those directions. So it's better not to choose if the two fine-tuning are going in two contrastive directions. So it's better to keep the pre-trained.
In all these methods, that it does it make sense to fine-tune the final model?
Well, it can give you an initial checkpoint. It can give you an initial checkpoint, but basically, well, let's take a look. If you can, yes, if you can, but it's not always the case. So let's suppose you don't have your final data and you just get your task factors or checkpoint from independently trained model from different people or different location even. So you don't have the final data, you cannot update that. But otherwise, it's obviously a good it's definitely a good initialization. It's the best probably initialization you can have. But you're not missing so many points in terms of accuracy just by merging things like that. So at TICE, it's very competitive, especially on very huge models. And again, you can combine TICE with another technique which is called DARE, and it's very funny because it comes from a paper that it's called Language Models Are Super Mario. I don't know why, but it's like this. What is the idea behind DARE? Is this one. Let's think about an LLM, and you know that an LLM is over-parameterized. And since it's over-parameterized, merging all the parameters may create some conflict direction. So what we are doing in this case is we randomly drop a certain percentage of parameters, a percentage that can be pretty high, 30%. We drop them to 0, and then we rescale the remaining one in order to keep the same statistics, like in the batch norm. So I want that the average of the weights is the same. And just by doing so, and since you are doing basically at random, what we are doing is creating some sort of disentangling in the parameter space if the model is redundant. So merging it's easier because you disentangle the space and you reduce the number of interference. And you can combine it with TICE. So before you disentangle the space and then you apply the TICE merging, and this combination is pretty popular and it's called direct TICE. And it's a very, very strong baseline in terms of model merging, okay? Well, the word is not all here. I'm just showing you the baselines, okay? There are plenty of very, very complicated methods that can be on top of it. I'm just showing you for every strategy a baseline, which is the task arithmetic in the case you linearize the model, which is the TICE in the case you have different checkpoints, but you cannot touch the model during the training. And we will see another one, which is called TSB. And again, here, we cannot touch the model. So we have our task vectors. And what we are doing, we decompose the task vector with the SVD. So we have a set of orthogonal component in the matrix U, and we have the spectrum here, and we have the matrix V again, orthogonal component. This is for task 1, this is for task 2, and so on, and so on, and so on. And then what we do here is to get rid of some component in the spectrum, the one with the lowest value. So it means that those are directions which are not really meaningful in terms of information. Then we stack all those vectors together. So recompose a very huge matrix by stacking all those vectors together and getting back a single task vector, which is the merge of the task vectors. What is important here is that every time you remove one component from this, you must ensure that those objects here and those objects here, since they will finish in the same U matrix, they should be orthogonal each other. Because by construction, the SVD consider the matrix U in which every column is orthogonal and the matrix V in which every row is orthogonal. So if I'm attaching those two components here, those two are no more orthogonal with this one. So it's not a good matrix. So again, I need to perform orthogonalization here, and you usually do it through the Procrustes trick. Okay, so basically you use the Procrustes algorithm to compute the orthogonal version there. And just by doing so, you are merging the task vector this time using the geometry. And you obtain a combination of direction for which the spectrum stays I. So you pick the most important component of every task vector and you put them in the same space together. Okay, this is a basic method. We did last new RIPS a more advanced version that is specifically tailored for LoRa. It's called core space, and it's a little bit more complicated. But again, this is one geometric baseline for merging model, and it's very easy again to implement. You just need to compute the SPD for every task vector. You get rid of, let's say, 50% of the component from the spectrum, apply Procrustes, and create your one big matrices. The dimension stays the same because here is number of parameters. Here you can put whatever you want. And then here you can put whatever you want, and V is the same. So at the end, you have a matrix which is in the number of parameters. So you can apply it as the merged task vector.
Just an notation clarification, the deltas are equal to the
Is tau. Yeah, exactly. Okay, this means it works, but it works. And it works really well. So take a look at this. This is the common weight averaging, so the baseline. This is the task arithmetic into the linear space. This is the consensus task arithmetic, which is basically applying ties to task arithmetic. And this is the TSV. And you can see that the improvement is significant. It's very significant. And here we are merging 8 tasks, here 14, and here 20. So when I'm saying about we are merging models, we can merge a lot of models. It's not just by 2 or 3. You can merge 20, 30, 40 of them. The number of models depends also on the size of your pre-trained network. So the smaller it is, the less model you can merge before it saturates. The larger it is, the more model you can merge. An additional trick, and this is a real magic. So I'm shaking hands to the author, but Daniel, that I also know pretty well, is this one that can be applied also to TSV or to whatever spectrum method you want to use. Instead of using the original spectrum, so after the selection of the component, when you rearrange the matrix, instead of using the original spectrum, what you do is substitute every singular value with the average of all the singular values. So you make a flat spectrum. This means that you are making the function represented by the SVD isotropic. So it takes the same importance for all the direction. And just by making isotropic, it seems that merging performs quite better. And it's just a small trick that gives you a few points. Okay, questions? Too easy? No? Okay. Okay, so just few words and then we are concluding. First thing first, okay, let's suppose I'm quite good at merging models. Which merging method should I choose? What are the things that I keep in mind when selecting a merging method? And there are basically 3 things. So the first one is that even if my multitask learning is my objective, it may happen that I should also take a look at the quality of every single task performances. So my idea is that I should retain every single task performances, but I should also increase the generalization capability of the model. If you remember the beginning, when we introduced the reason why we are merging stuff, is because picking the average of the solution is more probable to reach a low area of the test loss, not of the training one. So I should still be able to generalize a little bit, but I should also keep in mind that I still want to retain the original task performances. So basically, I want to behave as a multitask mode.
However, in a multitask setup, perhaps your final model will perform better in one of the tasks and worse in another one.
Yeah, exactly.
So it could be, it's some guarantee about the Pareto dominance, or
Not exactly. Okay. I have a slide later. The second problem is this one, and you should keep in mind the fact that you can perform the merging in a data-free way or in a data-dependent. Data-free, we have seen ISO, Dare, PSV, TICE, okay. Data-dependent, we have seen Fisher, mean, even task arithmetic, somehow it's data-dependent because you need to fine-tune and so on. So depending on the availability of data, you can select one set of models instead of another one. And it is a strong hypothesis here. Sometimes you don't have the data. Sometimes you don't want to use the data. Sometimes you cannot use the data. The third thing is, how resilient is my soup when I'm increasing the number of experts? Surprisingly, it seems that if your starting model is big enough, increasing the number of experts always increase the performances. So it's quite surprising for me, because if you think about merging, you're merging directions, so increasing the number of directions, it should be more probable to find two contrasting directions, so basically worsening the performance somewhere. Instead, this does not happen because a lot of the model we're using right now tends to be strongly over-parameterized. Why? For a lot of reasons, but basically because modern deep learning, but since the beginning of deep learning, does not care so much about the architecture efficiency. They just put a lot of parameters here and they regularize the training. But it means that the parameter stays there. So you are not using them during training, okay? You're avoiding overfitting, but architecturally, the network stays the same. So if you pick an LLM, billions of parameters, and so without surprise, the 50% of them is active, more or less. The other are copy or redundancy of the parameters you have so far, but they did a lot of experiment in this direction. So you can get rid, there are certain LLM, there was a paper 1 year ago that, well, get rid of 70% of the parameters of the LLM and the performance stays the same.
Is there any work that assess the performance in live models that for extra?
No, I don't think so, because in this case, it's very tricky. So the less parameters you have, the more difficult it is to merge the models. So what you usually do in the edge world, what I've seen so far in the edge world was doing something like this. Let's suppose I have a big pre-trained model. I'm doing it in FPGA. So it's no more deep learning models, it's hardware. And then you are treating the task vector as the software part of the problem. So in this case, you can still perform merging, and you don't have the problem of deploying a network on a general purpose hardware. And you can quite easily create your specific hardware and then plug in new capabilities just by adding the task vector there. This is an approach I've seen so far in the edge about model merging. Otherwise, the more your network is effectively using all the parameters, so the smaller it is, the more difficult it is to perform the merging, because every merge you are doing, you're adding some sort of knowledge. And you need to allocate the space for this knowledge, basically.
And it's a network where you did weight planning, which resonates a little bit with the drop of weights that you mentioned. Does it?
Yeah, obviously. If you perform some sort of pruning, so you create space for the merging, you can merge.
You still have the weights, but they're like empty.
Exactly. Last thing is, if your model is enormous, so the biggest as possible, the merging technique doesn't matter so much. So since the number of parameters is so redundant, and there are a lot of direction that stays there, even if some other are ruined by the merging, you can even use simple averaging, and it typically performs quite similar to the other. There's still a little bit of improvement in using a little bit more sophisticated method, but basically, as you can also see there, the differences tends to reduce a lot. Okay, the last thing you should pay into attention is your gap with respect to the multitask. So again, here we have a very large model, and I can combine those two knowledge together, okay, without sharing information between us in a total asynchronous way. And this is pretty useful because it allows to combine the knowledge of different neural networks independently trained without sharing the data. It's not exactly federated learning because federated learning is slightly different. It's some sort of asynchronous federated learning. If you just pass me the term, it's not learning because you're doing it at the end and not at every checkpoint, but basically it's something that is very similar. So it goes in the direction of why federated learning is typically applied in neural network learning. Okay. Give me 2 slides. Right now, yes. Okay. It is a strong assumption, but not too strong. So if you think, for example, a lot of neural network in 3 or 4 years ago start from ResNet 50. And now a lot of neural network starts from, I don't know, the visual encoder of CLIP or Dino V2 features. So in terms of backbone, most of the time, the architecture is not so different. A different pair of shoes is that if you are considering, I don't know, an LLM 20 billion and an LLM 6 billion, and you want to merge information between them, this is a slightly different problem. But in terms of model merging, well, at least the backbone most of the time stays the same. Okay. Just to give you a real example, there's this model which is called Common Day, which is a model that was trained in academia, I guess. And just by using model merging, it outperformed at the time GPT-4o. Just by merging different experts, everyone, you cannot see it, but you can see it right now. So everyone fine-tuned on a specific task. So you have the expert for RAG, the multilingual expert, the expert for math, the expert for code, fine-tune on the specific task, and then you merge them to a model soup, and then you fine-tune the soup, and what you obtain is a very, very strong model. Okay, so the last question, and then I have finished, is what if the foundation model changes? So what happens if the architecture changes over time or between models? So in this case, our idea was this one. Let's suppose I start from a foundation model, an LLM or a visual foundation model, and in my company, I've fine-tuned it for a lot of tasks. I'm selling it. I'm making money out of it, but then after a while, a new backbone, which is definitely better than the past one, appears. And typically, those backbone does not share the same architecture. So let's suppose, I don't know, it was my LLM with 6 billion, and now it's 24 billion or 30 billion, or the opposite. It was 24, now it's 6. I don't know, but usually those architecture does not match. Even if they match in terms of functional components. So let's suppose those are two transformers, but they do not match in terms of feature, fan in, fan out, and number of parameters, and number of blocks, and so on. So the architecture are totally disaligned. So is there something I can do? Because this is the most extreme case in which every parameters means something different. So this is the worst case in which I can apply model merging. Yes, we can do something. That's basically the case in which, in this paper, we deal with the attention module. And when you perform the attention module, you should keep in mind that the attention head are not aligned. So the attention head of model A, the first one, and the attention head of model B means something different. So the order is not the same. It's like the kernel in a convolutional neural network. So the order is not guaranteed there. So what you need to do is, before aligning the parameters through the permutation, is also to align the attention heads. The problem is that you should align them on the basis of an hypothetical alignment of the parameter. So you should find a cost measure that is invariant to all the possible permutation you can apply to the weights. And this is a little bit tricky. So we select the spectral measure, we define a measure which is invariant to the permutation. So we solve this alignment problem just by taking an alignment procedure, so like global alignment, like the one you use for DNA or for aligning sequences, but with a cost matrix that is invariant to the permutation. So basically, you can apply whatever permutation you want, and the cost of aligning stays the same. And when we align, after we have aligned the head, we can align the weights, so making them meaning the same stuff, and we can then merge them just by taking the arithmetic. This does not call for different architectures. We have sent an ICML paper right now about different architectures. And again, here you have to deal with one more challenge, that is the fanning of the features. Usually when you deal with different architectures, you have, I don't know, a token which is represented by 100 features in model A and 600 in model B. And it means that you have, I don't know, 30 or 40% of parameters of model B that should be created by nothing in order to match model A. And this makes things a little bit more complicated. And I think to my knowledge, it is the first paper that deals with different architectures. So I didn't see anything else right now. Let's see what happens. Okay, but it can be done. The performances are not as good as the model merging in the same architecture case. But again, answering your question, it gives you a very good checkpoint to start with by fine-tuning. It's definitely better than starting from scratch. It's definitely better than starting from each one of the two modules. So you typically converge very, very fast, and you typically regain all the performances you have lost through the merging. Okay. That's it. I want to thank those guys because the presentation was strongly inspired by their new RIPS tutorial. And these are three excellent scientists at the Vector Institute. We did some work together, and he's also from Modena. So and the guys that helped me just by doing this. Okay, I'm open to question. Let's suppose you are still awake.
We are. Yes, we are.
Okay.
Can you hear me?
I can hear you.
All right. Are there any questions in the room or online?
In the room? No question. You just want to go. No, I can hear him, and that's it. But he said, are there any questions in the room?
Well, here online, what we've been saying all the time is a poster that you have behind you that says, focus now, siesta later. So we've been really focused all the time, and we didn't sleep at all. So we actually paid attention, although there is Oh, there is a question actually from June that came up kind of at the very beginning when you were talking for the very first time about the model soup and the averaging, the classical one. And it is in the chat.
Just wait
I
a
can
second.
read it
Let's
out for
try
you
to
if you
fix it
want.
because I'm the only one that can hear you. So it's starting to be a little bit weird.
Oh, because you have, okay, I see. All right, can you hear me? Can you all hear me now?
Just a second.
There you go. Hello?
Yeah, we're gonna hear you.
Okay. June, if you want to unmute yourself and go with your question. So it was all about the very beginning of your talk, Simone, in which you were talking about averaging, like with this model soup, the initial approach. And June was wondering about that, and I guess imbalance class distribution. Maybe June already left. Otherwise, I read it for you.
I feel like you come here way too.
Okay, do you have the microphone turned on here? Okay. So what was the question?
So the question goes like, would this form of ensembling risk silencing models that are specialized for minority classes distribution by letting majority predictions dominate the aggregated output?
This is probably true, but I have a question for June. Is this a problem? So in the sense that obviously if you merge the models that you use, for example, like in the case of Fisher, so you're using the certainty you have about some parameters. Obviously, the parameters that have trained more are more certain, and the parameters that you train less are less certain. And when you deal with the minority classes, so you means that are classes that do not have a huge number of samples. I guess this is what is referring to. So it means that they did not contribute so much to the gradient descent. So it probably generates parameters that are not so strong. But again, you should, when you perform merging, it's not like you are doing the artisan. So you want to do things very pretty with very much of detail. What you want is the big bullseye. Okay. So at the end, what you want is that the general performances of the merge, and would you merge 20, 30, 40 models are good on a very huge data set. And so this is exactly the opposite direction of having minority classes. But even in modern LLM or modern foundation model, the concept of minority classes does not exist anymore. So the minority classes does not exist end of the day. So if you pick an LLM, a commercial one, let's suppose there are 10 texts over the internet that mention a specific topic, just 10 of them, they're not there. They were overwritten by the knowledge containing other millions of text. So what is the minority representation in the dataset? It's not coherent with modern foundation models. You can still achieve it by fine-tuning it. So if you have so few data, just perform model merging, get your very nice checkpoint, and then fine-tune it. Or use zero-shot technique or use few-shot techniques, again, to regain some sort of performance you have lost during the model. But when you're dealing with such huge models, start thinking about few samples of things that has been trained for a very few iteration of the gradient descent. Typically, when you merge them, they just disappear. The point is, I don't think it's a problem.
Good. So hopefully that's clear for June, although he did not reply yet. So I have one more question for you, Simone. So I was wondering when you were talking about models being over parameterized, right? And then you said that's actually really good for you to do the merging and being able to drop a big percentage of that. But then I was wondering, how does merging, the way you do it, could relate, or if at all possible, with mixture of experts? Could you not try to end up with a sparse network that would be dealing with different tasks in different subsets of the network or something like that? I don't know if that's making any sense to you, but
well, if I remember correctly, I'm not the expert of the mixture here, or the expert of the mixture of experts. But if I remember, in the mixture of experts, there's also some sort of routing function. Is it correct?
Yeah, you do need the router, yeah.
While here, instead, you don't have.
Yeah.
So think about that. Through the pre-training, your merge can share information together. While in the case of the mixture of experts, you're choosing the best one. So it means that you still don't have transfer between the expert, except for during the backpropagation, but it's a very light transfer in this case. While instead here, you can transfer between the models. So think about the plot I've shown you at the beginning, in which we had the checkpoints and the loss landscape of the test, and the solution was in between. Okay, this can be achieved by merging parameters, but it cannot be achieved through routing, because routing lets you select either checkpoint 1 or checkpoint 2, but you cannot go in between. Okay, did I answer?
No, definitely, yeah, really good.
Oh.
Thank you.
10 points per.
Yep. All right. Is there any other question from anyone in the room?
Perhaps I'll do.
I was gonna go with the basic one, but you already answered that one about trying to merge from different architecture, but you're already working on that. So, so yeah. So we will have to wait for your paper to be published at some point.
Okay. Hopefully.
Hopefully,
yeah. For me, a lot of good karma for us. So let's see what happens. Okay, thanks to everybody.
Thank you very much, Simone.
Congratulations. We will meet at 8:30.
Yes.
In the dinner.
For those of you coming to the tapas night, 8:30, Plaza del Campillo, number 1, I think. And so we'll meet there. Otherwise, 9 a.m. tomorrow, we should be there in person. So 9 a.m. for registration, okay?
Okay, great.
Thank you very much.
Isaac, te llamo por WhatsApp. Bye.
Bye.